Look up at the night sky and find that steady, rust-colored point of light. For centuries, that world has captured our imagination, a blank canvas for our hopes and our fears. We've mapped its canyons that dwarf our own, traced the outlines of its colossal volcanoes, and even driven our robotic explorers across its dusty plains. We call it the Red Planet, and it feels, in many ways, like a neighbor. Yet, for all the data we've collected, for every stunning image beamed back across millions of miles, Mars holds onto its secrets with a quiet, stubborn resolve. It presents us with a beautiful paradox. The more we learn, the more we realize just how much we don't understand. Beneath that familiar, reddish hue lies a world of profound and puzzling mysteries. Today, we are setting out on a journey to explore the Martian anomalies, the phenomena on Mars we simply cannot explain. This isn't a story with all the answers. This is the story of the questions themselves. It's a detective story written in the geology of an alien world, a scientific puzzle box waiting to be unlocked. We have sent our most advanced technology to act as our eyes and hands, rovers that function like field geologists and orbiters that scan every inch of the surface from above. They have sent back terabytes of information, and yet within that flood of data lie dozens of head-scratching, logic-defying observations. From geological formations that shouldn't exist to atmospheric behaviors that contradict our models, Mars is constantly challenging what we think we know. This video is an invitation to join that investigation, to look over the shoulder of humanity's collective curiosity as we confront these enigmas. We will wander through deep valleys where something strange is happening in the soil, gaze upon landscapes that seem to tell two different stories at once, and examine evidence that sparks more debates than it settles. Forget what you think you know about our celestial neighbor, because we are about to dive into the deep end of Martian mystery, exploring the 30 most compelling phenomena on Mars that continue to baffle the brightest minds in planetary science. Our journey into the unknown begins not with a grand landscape, but with something we can't even see, a whiff of gas. For years, our orbiters and rovers have been detecting sporadic plumes of methane gas in the thin Martian air, and this simple molecule has created one of the most profound and heated scientific debates of our time. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock, but it can also be created through geological processes like the interaction of certain rocks with water. So when our instruments on Mars sniff it out, the immediate, electrifying question is, which one is it? The puzzle deepens because methane shouldn't last long in the Martian atmosphere. Solar radiation and chemical reactions should break it apart within a few hundred years. Its persistent, flickering presence means something on Mars is actively replenishing it right now. It's as if we're walking into a kitchen and occasionally smelling freshly baked bread, but we can't find the oven or the baker. The Curiosity rover has been a key detective in this mystery, sitting inside Gale crater and repeatedly detecting background levels of the gas with occasional dramatic tenfold spikes. These aren't constant leaks, they are sudden, mysterious belches from the planet itself. Yet, adding another layer of intrigue, the ExoMars Trace Gas Orbiter, a sophisticated European spacecraft designed specifically to map atmospheric gases from above, has often reported that it sees very little methane on a global scale. This conflicting data is frustrating, but for scientists, it's a tantalizing clue. It suggests that whatever is producing the methane is not a widespread, steady process, but a localized and transient one. The methane seems to be appearing in specific places and then vanishing quickly, almost as if Mars is hiding the evidence. The search for the source is like a high-stakes treasure hunt. Is it the result of subsurface water reacting with olivine-rich rock in a process called serpentinization? Could it be the release of ancient methane trapped in ice like structures called clathrates, slowly melting and seeping out? Or, and this is the possibility that sends a shiver down the spine, is it a metabolic byproduct from subterranean Martian microbes, a silent, hidden biosphere whispering its existence to us? Every new data point pulls us deeper into the mystery, forcing us to question whether we are witnessing the mundane geology of an alien world or the first faint signature of life beyond Earth. From the tantalizing whispers of atmospheric methane, we turn our gaze to the very ground of Mars, to steep crater walls and canyon slopes where the planet itself seems to be bleeding. These are the recurring slope lineae, or RSL, and they present a visual spectacle as compelling as any mystery we've encountered. Imagine staring at a satellite image of a sun-baked hillside. As the Martian seasons turn and temperatures rise, dark, finger-like streaks begin to materialize, stretching tentatively downhill from rocky outcrops. They lengthen over weeks, sometimes for hundreds of meters, creating patterns that look for all the world like water trickling down a dusty pane of glass. Then, as the warmth fades, these enigmatic streaks gradually vanish, only to reappear in the very same spots when the heat returns the following year. This cyclical behavior, this apparent flow, immediately sparked a revolutionary and thrilling hypothesis. Could we be seeing liquid water in the here and now, actively seeping just beneath the Martian surface? The initial evidence seemed to support this incredible idea. Spectrometers on orbiting spacecraft detected the chemical signature of hydrated salts minerals that have water molecules bound within their crystal structure precisely at these RSL locations. The theory painted a vivid picture. It suggested that just below the surface, deposits of salt could be pulling tiny amounts of moisture from the incredibly thin Martian atmosphere, forming a super salty brine, a liquid that could remain unfrozen even at Mars's frigid temperatures. This brine, the idea went, would periodically seep out, darkening the soil as it flowed downhill before quickly evaporating or refreezing. For a world declared arid and frozen for eons, the implication was staggering. If liquid water was flowing on Mars today, even in this fleeting, briny form, it would radically reshape our understanding of the planet's potential for habitability. It would mean that the most crucial ingredient for life as we know it wasn't just a relic of a distant, wetter past, but a contemporary feature of the Martian environment. The search for life would have a vibrant, modern target, yet in science, a beautiful theory can be undone by an inconvenient fact. As more data poured in from high-resolution cameras and other instruments, the water hypothesis began to face serious challenges. The streaks were appearing on some of the steepest, most unstable slopes imaginable. If they were truly dampened by liquid water, even a small amount, you would expect to see some sign of the soil being moved, tiny channels, deposits of sediment, or other hallmarks of fluid flow. But no such features were found. The RSLs seemed to be merely a surface stain, a darkening without any discernible change in the topography. This led to an alternative and perhaps more sobering explanation: dry granular flow. In this scenario, the RSLs are not caused by water at all, but by the natural movement of sand and dust. The idea is that on these incredibly steep slopes, the warming sun causes small avalanches of fine, dark sand grains from outcrops at the top. As this dark sand cascades down over the brighter, dust-covered slope, it creates the temporary, dark streaks we observe. The seasonal timing could be explained by changes in atmospheric pressure or the sublimation of tiny amounts of frost that temporarily stabilize the slope, with the warmth triggering the collapse. So we are left with a classic Martian dilemma, a true scientific standoff. On one side, we have the compelling chemical signature of hydrated salts pointing toward water. On the other, we have the geomorphological evidence that suggests a simple, dry avalanche. The debate is far from settled, and every new observation seems to add a twist. Some scientists now propose a hybrid model where minuscule amounts of water, just enough to cause the chemical changes but not enough to significantly erode the soil, could still be the trigger. This unresolved puzzle makes the RSLs more than just a curious geological feature. They are a priority one target for future exploration. Landing a rover near an active RSL site is a dream for astrobiologists, though it comes with immense planetary protection challenges, as we would not want to contaminate a potentially habitable environment with Earth microbes. For now, these dark, flowing fingers remain one of Mars's most visually arresting and intellectually frustrating mysteries, a stark reminder that even what looks like a straightforward sign of water on another world can be a master of disguise. Moving from the subtle chemical whispers of methane and the ambiguous flows on crater slopes, we arrive at a mystery that is perhaps the most iconic in the entire history of Martian exploration, one born not just from data but from a powerful human impulse. In the summer of 1976, NASA Viking 1 orbiter was systematically mapping the Cydonia region of Mars, a vast plain of eroded mesas and buttes. Among the thousands of images it beamed back to Earth was one, frame 3572, that would ignite a firestorm of speculation and capture the global imagination for decades. There, in stark black and white, was what appeared to be a colossal humanoid face over 2 miles from end to end, staring stoically up from the Martian desert. It had what looked like 2 evenly spaced eyes, a distinct nose, and a mouth set in a faint, enigmatic smile. The initial NASA caption released to the press noted the feature's resemblance to a human head, a simple observation that, in the cultural context of the 1970s, was like throwing a lit match into a room full of fuel. The idea of a long-lost Martian civilization, one capable of carving a monument on a planetary scale, exploded into the public consciousness. It was featured on the covers of tabloid newspapers, inspired countless books and documentaries, and became a central pillar for a new wave of belief that Mars held the secrets of our own ancient past. The face on Mars was no longer just a geological formation. It became a symbol, a question mark etched into the landscape of another world, challenging our place in the universe. For scientists, however, this single, low-resolution image was always a source of profound skepticism. They argued it was a classic example of a natural landform, a mesa, seen under dramatic, low-angled lighting that accentuated shadows and created the illusion of facial features. The debate raged for over 2 decades, a standoff between public wonder and scientific rationale. The turning point came with a new generation of orbiters equipped with cameras of breathtaking power. When NASA Mars Global Surveyor turned its high-resolution lens toward Cydonia in 1998 and again in 2001, it delivered the definitive verdict. The new images showed with crystal clarity not a sculpted face but a heavily eroded, windswept hill. The once perfectly symmetrical eyes were revealed as rocky pits and shadows. The nose was a central peak, and the entire structure was littered with boulders and debris, its features the result of millions of years of natural erosion. There was no doubt the face was and always had been a trick of the light and perspective, but to simply say "case closed" would be to miss the deeper, far more fascinating mystery revealed by the entire episode. The real phenomenon wasn't on Mars at all, it was happening inside our own brains. What we witnessed was a powerful demonstration of pareidolia, a hardwired psychological tendency to perceive a familiar pattern, especially a face where none actually exists. This isn't a flaw, it's a fundamental survival mechanism. Our brains are exquisitely tuned to recognize faces from just a few clues because quickly identifying a friend or a foe was crucial to our ancestors' survival. This instinct is so strong that we see faces everywhere in the swirls of wood grain, the contours of a cloud, or the front end of a car. Mars, with its vast, silent, and unfamiliar landscapes, is the ultimate canvas for this projection. The story of the face on Mars, therefore, transcends a simple geological explanation. It teaches us a profound lesson about exploration and perception. It shows how our deep-seated desire to find companionship in the cosmos, to believe we are not alone, can shape what we think we see. The feature became a cultural icon not because of what it was, but because of what it represented to us: a beacon, a signpost, a message. It fueled public fascination because it tapped into a universal hope, a narrative far more compelling than that of a windswept hill. And in a strange way, even though it was an illusion, the face on Mars served a vital purpose. It brought the red planet into the daily conversations of millions, galvanizing public interest and arguably helping to build the support that led to the fleet of sophisticated rovers and orbiters we have there today. It stands as a permanent monument not to a lost Martian civilization, but to the boundless and sometimes creatively mistaken curiosity of our own. From the psychological intrigue of the face on Mars, we journey to a much smaller, yet equally captivating mystery, one that was discovered not from orbit, but right under the wheels of a rover. When the Opportunity rover bounced to a stop in Eagle Crater in 2004, its cameras revealed a landscape that was immediately alien. The fine, reddish soil was littered with countless tiny, grayish spherules no larger than ball bearings. Scientists at the mission control were so taken by their appearance that they quickly dubbed them blueberries, despite their gray color inspired by their small, round shape. But these weren't just pretty rocks. They were soon identified as hematite concretions. Hematite is an iron oxide mineral that, on Earth, most often forms in the presence of liquid water. It was a monumental clue, the first direct, on-the-ground evidence that this part of Mars had once been soaked. The discovery was like finding a fossilized raindrop on a desert floor. It spoke of an entirely different climate, a different world. The theory of their formation is a story written in water and chemistry. Billions of years ago, when groundwater was flowing through the porous sandstone layers in this region, it was rich in dissolved iron. As the chemical conditions in the water changed, perhaps due to interactions with other minerals or a shift in acidity, the iron could no longer stay dissolved. It began to precipitate out, solidifying around a central nucleus like a grain of sand. Layer by microscopic layer, these concretions grew, much like how an oyster forms a pearl. Then, over eons, the softer sandstone surrounding these hard, resilient balls of hematite eroded away, leaving them scattered across the surface like marbles spilled from a bag. They are, in essence, the durable remnants of a long-vanished aquatic environment. Yet, for all we understand about the basic process, the Martian blueberries hold onto specific puzzles that continue to intrigue geologists. The first is their remarkable uniformity and near-perfect sphericity. While concretions on Earth come in all sorts of shapes, disks, tubes, and irregular lumps, the ones in Meridiani Planum are overwhelmingly and exquisitely round. This suggests the conditions under which they formed were incredibly consistent. The water must have been uniformly saturated with iron, and the chemical process must have occurred equally in all directions around the nucleus for millions of years without significant interruption. It points to a stable, long-lasting, and widespread groundwater system, a hydrological environment far more persistent and organized than we might have previously imagined for early Mars. The second puzzle is their staggering abundance and specific distribution. Opportunity didn't just find a few clusters, it found them by the millions, carpeting vast areas. In some places, they were so densely packed that the rover's wheels would crack them open, revealing a concentric internal structure. Why here? Why in such incredible numbers? This suggests that the particular patch of Mars where Opportunity landed was a veritable hotspot for this specific chemical process. It might have been a focal point for groundwater discharge, a place where the chemistry was just right for concretion formation on an industrial scale. Some scientists have proposed alternative formation theories that challenge the simple, slow groundwater model. One intriguing idea is that the blueberries could have formed directly from the interaction of acidic, iron-rich surface water with volcanic ash, a process that might create such perfect spheres more rapidly. Another theory suggests they could be the result of a meteorite impact where superheated fluids circulated through the fractured rock. While the water-based concretion model remains the most widely accepted, these other hypotheses highlight that we cannot yet rule out a more complex or even catastrophic origin story. What makes the blueberries a lasting phenomenon rather than a solved case is that they represent a specific, highly efficient geological process that we have not seen replicated elsewhere on Mars with such purity and density. They are a unique signature of the ancient environmental conditions in one particular region, a testament to a time when the chemistry of rock and water on Mars created something both beautiful and profoundly mysterious. They are tiny, ironclad time capsules, and while they confirm the presence of water, they also left us with a deeper question. What exact set of perfect, planet-wide circumstances led to this one landscape becoming a factory for billions of perfect little spheres? Leaving behind the tiny, iron-rich marbles scattered by opportunity, we now shift our view to a geological wonder of an entirely different scale, one that dwarfs anything we've discussed so far. Stretching for over 5,000 kilometers along the equator, the Medusa Fossae formation is arguably the most enigmatic and extensive deposit on the entire planet. From orbit, it appears as a vast, softly contoured, and almost dreamlike landscape, a blanket of material so profoundly thick and mysteriously erodible that it has completely reshaped this part of Mars. It's a formation that doesn't just pose a single question, but a cascade of them, challenging our most fundamental ideas about Martian geology and climate history. The first and most immediate puzzle is its sheer volume. The Medusa Fossae formation is not a thin veneer. In places, it's estimated to be several kilometers thick. To put that into perspective, if you could stack it up, this single geological unit would be deeper than many of the tallest mountain ranges on Earth. The sheer amount of material involved is staggering, and the immediate question is, where did it all come from? What colossal process could possibly lay down such an immense and uniform blanket across such a vast swath of the planet? Adding to the mystery is the material's bizarre physical nature. It is exceptionally soft and easily eroded by the Martian wind. Over millions of years, the persistent, sand-blasting winds have carved the formation into a spectacular, almost surreal terrain of sinuous ridges, deep yardangs that look like the hulls of overturned ships, and strange, elongated mesas. This intense sculpting tells us that the substance making up the Medusa Fossae is incredibly weak, far weaker than the solid volcanic basalt that covers much of the planet. It has the consistency of a compacted powder, something that could be easily scooped and crushed in your hand. This leads directly to the central debate: what precisely is this stuff? For a long time, the prevailing theory pointed to the giant volcanoes of the Tharsis region, which lie to the west. The idea was that the Medusa Fossae formation represents the largest volcanic ash deposit in the entire solar system. Imagine a series of apocalyptic eruptions, far more powerful than anything in recorded human history, spewing colossal volumes of fine ash and pumice high into the Martian sky. Prevailing winds could have then carried this immense plume and deposited it evenly across thousands of kilometers, creating a deep, soft layer that later hardened just enough to hold its shape while remaining vulnerable to erosion. Data from orbital radar sounders seem to support this, showing that the material has a very low density, consistent with porous, ash-rich rock. But the volcanic ash theory isn't without its problems. The composition, as measured from orbit, doesn't perfectly match what we'd expect from the Tharsis volcanoes. It's rich in sulfur and chlorine, which fits a volcanic origin, but its exact mineralogy remains curiously ambiguous. This has opened the door for a compelling and radically different hypothesis, that the Medusa Fossae is not a product of fire but of ice. This alternative theory suggests the formation could be a gigantic pile of friable lead dust cemented by ice. The idea is that during different climatic epochs, when Mars had a greater axial tilt, ice and snow could have accumulated massively at the equator. This ice would then act as a glue, trapping immense amounts of wind-blown dust into a thick, frozen layer. Over time, as the climate shifted again and the ice sublimated away, turning directly from a solid to a gas, it would leave behind an incredibly weak, porous skeleton of dust, a material perfectly predisposed to being carved into the fantastical shapes we see today. Some scientists even propose a hybrid process, a kind of dusty avalanche called an ice seal, where mixtures of ice and dust flowed across the landscape, depositing this strange material. The debate between the fire theory and the ice theory is far from settled. Each explains some aspects of the formation perfectly while struggling with others. The volcanic model elegantly accounts for the volume and the low density, but has trouble with the global chemistry. The ice-rich dust model explains the easy erodibility and some of the strange flow-like features, but has a harder time explaining how such a uniform deposit could be laid down across such a vast area. The true answer likely holds profound implications. If it's mostly volcanic ash, it tells a story of a Martian past dominated by volcanic fury on an almost unimaginable scale. If it's an ice dust deposit, it paints a picture of a dramatically different climate, with ice ages at the equator that make our own planet's history seem tame. The Medusa Fossae formation, therefore, is more than just a beautiful landscape. It is a deep time archive, a cryptic record of the most powerful forces that have shaped Mars over billions of years, and we have only just begun to learn how to read its pages. As we continue our journey across the red planet, we travel from the immense, wind-sculpted plains of Medusa Fossae to a landscape of almost alien intricacy at the Martian South Pole. Here, a truly otherworldly phenomenon unfolds, one that looks less like geology and more like something straight out of a science fiction epic. Scattered across the frozen, carbon dioxide ice cap are vast fields of features known as areniform terrain, a scientific name that literally means spider-like, and the moment you see them, the reason for the name becomes chillingly clear. From high above, these formations appear as dark, sprawling, dendritic patterns, some spanning the length of a football field, with a central pit from which hundreds of thin, twisting and furrowed channels radiate outward. They do not merely resemble spiders, they look like a colossal, fossilized arachnid army frozen mid-crawl across the polar ice. This is not a case of pareidolia like the face on Mars. These are real, physical structures etched deeply into the Martian surface, and their formation involves a process so uniquely Martian that we have nothing even remotely like it here on Earth. The story of the Martian spiders is a tale written not in rock and water, but in ice and gas, a seasonal dance driven by the strange physics of the Martian climate. Each southern spring, as the sun peeks over the horizon after the long polar night, its weak rays begin to warm the landscape, but this warming doesn't act on water ice as it would on our planet. The south pole of Mars is covered in a thick slab of carbon dioxide ice, what we commonly call dry ice. And when sunlight hits this dry ice, it doesn't melt into a liquid. It undergoes a process called sublimation, turning directly from a solid into a gas. This is where the magic and the violence begins. Scientists believe that the sunlight is not just heating the surface, it's actually penetrating the translucent carbon dioxide ice, heating the dark, dusty Martian soil underneath. This heat then radiates back upward, warming the underside of the CO2 ice slab from below. As the bottom of the ice layer sublimates, it creates a tremendous pressure buildup. The gas becomes trapped, seeking any avenue of escape. Finally, the pressure becomes too great and the overlying ice fractures. The trapped carbon dioxide then erupts violently through these cracks in a jet-like plume, carrying with it a torrent of dark basal dust and sand. This dusty gas geyser shoots up into the thin Martian atmosphere and then falls back down, coating the bright ice around the vent with a dark, fan-shaped deposit that we can see from orbit. But the eruption does more than just create a dark stain. It actively carves the landscape. Over countless seasons, this explosive, gas and dust-laden jet acts like a sandblaster, relentlessly eroding the soft, underlying soil and carving out those intricate, branching channels that radiate from the central vent. It is a slow, methodical, and incredibly powerful sculpting process. The reason the patterns are so complex and spider-like, rather than simple circles or cracks, has to do with the nature of the pressure release and the substrate. The gas doesn't just find one single weak point. It follows paths of least resistance through the soil and the ice, creating a network of fractures. As the same spots are reactivated year after year, these fracture networks become more pronounced, deepening and widening into the permanent, arachnid leg channels we observe. The spiders are, therefore, not a static feature but a dynamic, seasonal event. Orbiting spacecraft have even captured the exact moment of their creation, spotting the dark fan-shaped deposits appearing suddenly during the spring thaw, direct evidence of the explosive geysers in action. What makes this a profound mystery rather than just a solved puzzle is the sheer uniqueness of the entire process. We have no carbon dioxide ice caps on Earth of this scale and permanence. Our geological processes are dominated by liquid water, wind, and tectonic activity. The formation of the areniform terrain is a purely Martian phenomenon, a direct consequence of the planet's thin atmosphere and its carbon dioxide-dominated climate cycle. It forces us to expand our library of geological understanding, to include processes that are, from our Earth-centric perspective, bizarre and counterintuitive. These spiders are a stark and beautiful reminder that other worlds operate by their own rules, and that sometimes the most familiar-looking shapes can be formed by the most alien of mechanisms. From the delicate, seasonal artistry of the polar spiders, we now confront a phenomenon of raw, planet-wide power. Imagine a storm so vast it doesn't just cover a continent, but engulfs an entire world. On Mars, this is not a fantasy. It is a recurring, awe-inspiring, and deeply mysterious event, the global dust storm. These are not the localized dust devils that dance across the plains, but apocalyptic-scale tempests that can shroud the entire planet in a tan haze for months on end, transforming Mars from a detailed globe into a featureless orange ball. The sheer scale is almost impossible to comprehend. A single such storm in 2001 raised atmospheric temperatures globally by a staggering 30 degrees Celsius, and the suspended dust blocked so much sunlight that it effectively turned day into a perpetual, eerie twilight. For our robotic explorers, these storms are a direct threat. The Opportunity rover's mission was tragically ended in 2018 when a global storm blocked the sun for so long that its solar panels could not recharge its batteries, leading to a permanent silence. But for scientists, these cataclysms present a fascinating puzzle that begins with a deceptively simple question. How does a storm that starts in a small, localized area spiral so completely out of control that it consumes a planet? The initiation of these global monsters is surprisingly humble. It often begins in the southern hemisphere during its spring and summer, when the planet is closest to the sun and receiving maximum solar energy. This intense heating creates extreme temperature differences between the warm ground and the cold air, fueling powerful winds. These winds lift fine dust particles from specific, easily erodible regions. At first, it's just a local dust storm, perhaps a few hundred kilometers across. But here is where the mystery deepens. On Earth, a storm like this would eventually run out of energy, encountering oceans or mountain ranges or simply dissipating. Mars has no oceans to break its momentum. The Martian landscape offers little friction, and the low gravity means the finest dust particles can stay suspended for an incredibly long time. The key seems to be a self-reinforcing feedback loop that turns a local nuisance into a global event. As the dust is lifted into the atmosphere, it doesn't just obscure the surface, it actively changes the atmospheric dynamics. The suspended dust grains absorb sunlight, heating the air around them. This creates a huge thermal imbalance, which in turn drives even stronger winds. These stronger winds then lift even more dust, which heats the atmosphere further, creating a vicious cycle of self-amplification. The storm, in essence, creates its own engine, a positive feedback loop that allows it to grow exponentially, spreading across latitudes until the entire atmosphere is choked with dust. Yet, for all we understand about this feedback process, our models still fail miserably at predicting when a local storm will trigger this runaway domino effect and when it will simply fizzle out. Why do some years see only regional storms while others, like 2001 and 2018, explode into planet-encircling events? This is the central, unresolved enigma. The answer may lie in the complex initial conditions on the surface. The availability of dust is not uniform. It requires vast reservoirs of loose, fine-grained material ready to be lifted. A global storm might only ignite if multiple local storms erupt simultaneously in key dust source regions, creating a critical mass that the atmosphere can no longer contain. Alternatively, it might depend on the specific mineralogy and size of the dust particles in a given season, which affects how efficiently they absorb solar heat and thus how powerfully they drive the feedback loop. There are even theories involving larger-scale atmospheric oscillations and dust seedings from the retreating polar ice caps. Our climate models for Mars, while sophisticated, simply don't have the resolution to capture these fine-scale tipping point events. We are trying to predict the planet's fever with a thermometer that is just not sensitive enough. The dust itself also holds secrets. Recent data suggests that the tiny dust particles may become electrically charged through friction as they collide in the atmosphere, potentially creating global electric fields that influence their lifting and transport in ways we are only beginning to understand. The global dust storm is therefore more than just a meteorological curiosity. It is the dominant force in the modern Martian climate system, a violent and unpredictable reset button that profoundly affects everything from atmospheric chemistry to the potential for future human exploration. Understanding its trigger is not just an academic exercise. It is a necessity for anyone who dreams of one day walking on a surface that can, without warning, vanish for months beneath a raging, sun-blotting shroud. Buried deep beneath the stark, frozen wastelands of the Martian South Pole, a discovery was made that sent shockwaves through the scientific community, a finding so profound it seemed to rewrite the very definition of a habitable environment. Using a sophisticated radar instrument aboard the European Space Agency's Mars Express orbiter, scientists peered for the first time through nearly a mile of solid ice, and what they detected was a signal unlike any other. The data revealed a patch of terrain about 20 kilometers across with a brightness and consistency that pointed overwhelmingly to one thing: a massive reservoir of liquid water. This wasn't a fleeting dampness or a thin film. The evidence suggested a stable, subglacial lake buried under the ice, a body of water that could potentially rival some of the smaller lakes here on Earth. The concept was staggering. Here, in one of the coldest places on Mars, where surface temperatures plummet to -110 degrees Celsius, a pocket of liquid water had somehow endured for eons. The secret to its existence lies in a combination of immense pressure and extreme salinity. The tremendous weight of the overlying ice cap creates pressure that significantly lowers the freezing point of water. More importantly, the water is thought to be not pure, but a supersaturated brine, a thick, syrupy liquid saturated with perchlorate salts, which can prevent water from freezing even at temperatures as low as -70 degrees. This created a picture of a dark, still, and intensely salty aquifer, completely isolated from the surface, a relic water body trapped in a state of deep freeze, yet fundamentally liquid. The immediate and electrifying implication was, of course, the potential for life. On Earth, we find extremophile microbes thriving in precisely these kinds of environments, locked away in subglacial lakes like Lake Vostok in Antarctica. These ecosystems exist in total darkness, cut off from the atmosphere, surviving on chemical energy from minerals in the bedrock. The discovery of a similar habitat on Mars suggested that life, if it ever arose, could have found a refuge, a place to retreat and potentially survive in a dormant state for millions of years. This underground lake wasn't just a geological curiosity. It was a sanctuary, a time capsule that might still be inhabited. However, as with so many Martian mysteries, this groundbreaking discovery was soon met with intense scrutiny and a wave of compelling counterarguments. The central piece of evidence, the bright radar reflection, is not a simple, unambiguous indicator of liquid water. The instrument works by sending radio waves down through the ice and measuring how much of that energy is reflected back. A very bright reflection, known as a high dielectric constant, typically indicates a material that is highly conductive, and liquid water, especially salty water, is an excellent conductor. But other substances can mimic this signal. The primary alternative hypothesis points not to a lake, but to a specific type of clay mineral known as smectites. These clays are layered silicate minerals that can also produce very bright radar returns, especially when they are cold and contain water molecules within their structure. Could it be that what was interpreted as a vast lake is actually a thick layer of these water-rich clays, a frozen, swampy sediment rather than a free-flowing body of water? Another possibility involves not a warm lake, but an even colder one composed of a special type of brine. Some laboratory experiments have shown that mixtures of water and certain salts can cool to extremely low temperatures and form a slushy, semi-solid state that is not liquid in the way we imagine, but could still produce a strong radar signature. This would be more of a frozen, muddy brine than a distinct lake, a much less hospitable environment for any form of life. The debate intensified when subsequent radar surveys of the area, including data from NASA Mars Reconnaissance Orbiter, struggled to find the same strong, continuous signal. Some of these follow-up studies using different radar instruments or processing techniques saw only patchy, weaker reflections, or failed to detect the lake's distinctive signature at all. This doesn't necessarily mean the lake isn't there, but it suggests the feature might be more complex, perhaps a network of smaller, saturated sediment pockets rather than one giant, coherent pool. The scientific community is now firmly divided, with passionate arguments on both sides. Proponents of the lake theory argue that the initial signal is simply too bright and too localized to be explained by clay alone, which tends to be more widespread. They point to the specific shape and sharp boundaries of the reflective area as being characteristic of a subsurface liquid body. The skeptics, however, maintain that extraordinary claims require extraordinary evidence and that the clay or cold brine explanations are more parsimonious, requiring fewer geological gymnastics. This is the rigorous, often messy, process of science at work, where a single, exciting data point is immediately stress-tested by the entire global community. The ultimate resolution of this mystery carries immense weight, not just for our understanding of Mars, but for the future of exploration itself. Verifying the existence of this lake is a monumental technical challenge. Peering through a kilometer of ice with radar from orbit is already pushing the limits of our technology. Directly sampling that water is a task of another magnitude entirely. It would require a mission capable of drilling through the immense ice cap, a feat never before attempted on another world, all while maintaining strict planetary protection protocols to prevent any contamination of this pristine, potentially habitable environment with Earth microbes. The engineering hurdles are staggering, but the scientific prize is unparalleled. A confirmed subglacial lake on Mars would be the single most important astrobiological target in the entire solar system, a destination that would redefine our search for life beyond Earth. It represents the tantalizing possibility that even today, in the most unlikely of places, Mars might still be holding onto a secret, wet and alive. Now, let's shift our focus from the planet's deep interior to its surface, where the winds of time have carved another set of haunting relics. Scattered across various regions of Mars are strange, crescent-shaped depressions, often arranged in long, sweeping lines that curve across the landscape like the footprints of a phantom army. These are the ghost dunes, and they are among the most evocative and telling geological features we've found. Unlike the active dunes that slowly march across craters today, these are not made of sand. They are the hollowed-out impressions, the negative spaces where gigantic dunes once stood billions of years ago. Their story is a multi-act play of burial, cementation, and exhumation, a process that required a very specific and dramatic sequence of events. It begins in an ancient Mars, a world with a much thicker atmosphere, one capable of generating powerful winds that could pile up immense sand dunes, some towering hundreds of feet high, rivaling the largest on Earth. Then a dramatic shift occurred, perhaps from volcanic ashfall or a blanket of water-rich sediments. These colossal dunes were completely buried. Trapped under this heavy overburden, the sand grains within the dunes underwent a remarkable transformation. Groundwater, rich in minerals, likely percolated through the buried sand. This water acted as a cementing agent, depositing minerals like silica or calcium sulfate between the sand grains, turning the loose dune into a solid, resilient cast of its former self, a sandstone structure preserving the exact shape of the original dune. Finally, in the modern era, the tables turned. The softer material that had entombed these hardened dune casts was itself stripped away over eons by the relentless Martian wind, a process of planetary exhumation. The once buried dunes were revealed again, but not as piles of sand. They stood as resistant ridges while the uncemented material around them vanished. In some cases, only the bottom portions of the dune casts remained, leaving behind those distinctive, U-shaped and crescentic footprints in the bedrock, the literal ghosts of dunes past. Their very existence tells us two profound things. First, it confirms that the ancient Martian atmosphere was indeed substantially thicker and more powerful than it is today, capable of moving the vast amounts of sand needed to build such monumental features. Second, it reveals a planet that has experienced violent climate swings, cycling through periods of active sand movement, deep burial, and then intense erosion. But the ghost dunes hold deeper, more specific puzzles that scientists are still piecing together. The central question is one of preservation. Why did some dunes become cemented while others presumably did not? The process seems to have been incredibly selective. The answer likely lies in the precise chemistry and timing of the groundwater flow. It suggests that cementation was a localized event, perhaps dependent on a specific water table level or a unique mineral composition in certain regions. This means these ghost dunes are not just random relics, they are markers of past oases of hydrological activity, places where the conditions were just right for this geological fossilization to occur. Furthermore, the orientation and shape of these ghost dunes are a frozen snapshot of ancient wind patterns. By analyzing their curves and the direction of their steep, downwind faces, their slip faces, scientists can reconstruct the wind directions that prevailed billions of years ago. This is like finding a fossilized weather vane from another world. The data paints a picture of a dynamic, complex climate system, with winds that sometimes align with modern patterns, but often do not, indicating major shifts in atmospheric circulation over Martian history. Perhaps the most tantalizing aspect of these features, however, is their potential as biological time capsules. On Earth, the interiors of sand dunes can create microhabitats. Their porous nature allows for the flow of water and nutrients, and the spaces between sand grains can shelter microbes from harsh surface radiation. If microbial life ever did gain a foothold on ancient Mars, the damp, protected interiors of these dunes would have been a prime neighborhood. And if those dunes were then hardened into solid rock, they could have preserved any potential microbial fossils in exquisite detail, much like the stunning fossilized microbial structures found in ancient desert sandstones on Earth. This makes the ghost dunes not just geological curiosities, but high-priority targets in the ongoing search for signs of past life. They are silent, sand-sculpted monuments to a lost world, holding within their stony curves the secrets of Mars's vibrant and ultimately vanished youth. If the ghost dunes feel like the fossilized imprints of a lost world, then the chaotic terrain is the portrait of its violent death. Across vast stretches of Mars, particularly where the southern highlands break into the northern lowlands, the ground appears to have simply fallen apart. We're not talking about gentle erosion here. This is geological anarchy. One of the most dramatic examples is Hydraeot's chaos, a sprawling region of utter disarray. From orbit, it looks as if a celestial titan took a hammer to the Martian crust, leaving behind a fractured landscape of thousands of isolated, blocky mesas, some as large as cities, adrift in a sea of jumbled valleys. The terrain is a labyrinth of disorder, a stark and unsettling contrast to the smooth volcanic plains that border it. The sheer scale of the collapse is staggering, and it points to a single, cataclysmic event that must have unfolded with almost unimaginable force. The leading theory to explain this planetary-scale wreckage is as dramatic as the landscape itself: the catastrophic release of groundwater on a scale that dwarfs any flood in human history. Imagine a vast, pressurized aquifer, a subterranean ocean trapped deep beneath a layer of frozen ground or thick, confining rock. Then, something happened to break the seal. Perhaps a volcanic intrusion melted the icy cap, or the ground was fractured by the immense shock of a massive meteorite impact. Once that seal was compromised, all hell broke loose. The pressurized water would have erupted to the surface in a colossal, raging outflow, destabilizing the entire region from below. The ground, suddenly deprived of its subsurface support, would have collapsed into the newly emptied voids, fracturing into the countless blocks and mesas we see today. The water, now free, would have gathered into a torrent of biblical proportions, a mega-flood carving immense channels as it thundered across the landscape, eventually draining into the northern lowlands. This isn't just a speculative idea. The evidence is written directly into the geography. These chaotic terrains are almost always found at the head of enormous, unmistakable outflow channels, like Aram Chaos feeding into Ares valleys, the very valley where the Pathfinder mission landed. It's a clear before and after picture. The chaotic terrain is the scar of the collapse, and the outflow channel is the path of the flood. The volume of water required to carve these channels is mind-boggling, estimated to be in the millions of cubic kilometers, enough to cover a continent. This leads directly to the profound and still unanswered questions at the heart of this phenomenon. First, what was the nature of the original reservoir? Where did all this water come from, and how was it stored? Some scientists propose a global layer of porous, water-saturated rock, a planet-wide aquifer. Others suggest the water was locked up in regional deposits of chaotic, ice-rich material, left over from a time when the climate was far colder. The exact source remains a subject of active debate because the volume of water involved pushes the limits of what we believe was possible for Mars to hold. The second, even more puzzling question is, what was the trigger? What specific event or process could have been so powerful and so widespread as to cause the simultaneous collapse of such enormous areas? A single, giant impact is one candidate, but the chaotic terrains are not always neatly associated with the largest craters. Widespread volcanic activity from the Tharsis region could have provided the heat to melt vast subsurface ice deposits, but the timing and the plumbing required are complex. Another compelling theory points to the process of cratering itself. Over billions of years, as large asteroids pummeled the planet, they could have fractured the crust to great depths, creating a network of weaknesses. Later, a climatic shift or a period of increased geothermal heat could have melted the ice within this pre-fractured crust, causing a cascading failure across entire regions. The chaotic terrain, therefore, is more than just a strange-looking landscape. It is the most direct evidence we have that Mars not only had vast quantities of water in its past, but that this water was unleashed in some of the most violent and transformative episodes in the solar system's history. It represents a planet cracking open and bleeding its lifeblood into the void, a pivotal moment that may have forever sealed the fate of a potentially habitable world. These layered deposits at the poles are not just simple caps of ice. They are the most detailed historical archive we have for the entire Martian climate, a sprawling, frozen library stacked with millennia of planetary history. If you could slice into them, you would see an astonishingly regular pattern of light and dark bands, a stark visual rhythm of ice and dust that stretches back for millions of years. Each pair of light and dark layers represents a single climate cycle, much like the yearly growth ring of a tree, but on a planetary scale. The lighter bands are primarily water ice laid down during one climatic period. The darker bands are much thinner and are composed of dust deposited during another. The sheer number and regularity of these layers tell us that the drivers of Martian climate are, and have always been, profoundly rhythmic and predictable. The primary engine behind this grand celestial metronome is a phenomenon known as Milankovitch cycles. These are slow, periodic changes in a planet's orbit and axial tilt, and they affect Mars even more dramatically than they do Earth. The tilt of Mars's axis, its obliquity, swings wildly over cycles of about 120,000 years. When the tilt is high, the poles receive more direct sunlight, causing the ice caps to sublimate and release water vapor into the atmosphere. When the tilt is low, the poles become colder traps, and that water vapor migrates back and freezes out, building up a new, clean layer of ice. Simultaneously, the eccentricity of Mars's orbit, how circular or oval it is, changes over longer periods, altering the intensity of the seasons. These combined orbital dances control the planet's thermostat, dictating when dust storms are more frequent and violent, which in turn determines how much dark dust is dropped onto the ice during each cycle. By simply counting these layers and measuring their thickness, scientists can effectively read the planet's past climate like an open book. A thick layer of ice suggests a long period of low obliquity, a deep freeze at the poles. A particularly dark and prominent dust band might correlate with a period of high obliquity and intense global dust storm activity, when the atmosphere was thick with suspended sediment that eventually settled everywhere, including on the pristine ice. This beautiful correlation between orbital mechanics and the layered record is a triumph of planetary science, allowing us to reconstruct a detailed climate history for a world we've never set foot on. Yet, for all its elegance, this frozen archive holds cryptic passages that we are still struggling to decipher. The first major puzzle lies in the exact composition of the dark, dusty layers. We know they are not pure dust, they are a complex mixture. But what minerals precisely make them up? Are they primarily volcanic ash, telling a story of ancient colossal eruptions? Or are they more common silicate dust ground down from the basaltic plains by eons of wind erosion? The specific mineralogy matters because it would point directly to the source of the material and the environmental conditions when it was deposited. Furthermore, within these dark layers, there could be traces of exotic salts or even organic compounds, clues that could hint at periods in the past when the polar environment was more chemically active and perhaps even habitable. The other, even deeper mystery involves the occasional anomalies in the layering itself. The record is not perfectly uniform. In some places, the layers appear warped, folded, or even interrupted entirely. What specific, dramatic climatic events do these distortions represent? Could a particularly powerful impact event have sent shockwaves through the ice, disrupting the careful deposition? Or do these irregularities mark a climate anomaly, a period where the normal Milankovitch rhythms were overridden by something else, One compelling theory suggests that the immense weight of the ice caps themselves can cause the underlying crust to sag, altering the local topography and skewing the subsequent layer deposition. Another idea points to periods of extreme volcanic outgassing from the Tharsis region, which could have temporarily thickened the atmosphere, changed global wind patterns, and deposited a unique, geochemically distinct layer of material that doesn't fit the normal pattern. Unraveling these anomalies is like finding a ripped page in the history book. It tells us that while the long-term climate is dictated by orbital cycles, the short-term story can be violently unpredictable. The polar layered deposits are therefore a paradox. They are both a clear record and an encrypted one. They confirm the powerful, rhythmic heartbeat of the Martian climate, but they also preserve the scars of its moments of planetary fever, its sudden upheavals and silent catastrophes. From the chaotic aftermath of planet-wide floods, we turn to a phenomenon that is far more subtle and seasonal, yet no less strange. As winter's grip tightens on the Martian poles and mid-latitudes, a layer of carbon dioxide frost blankets the landscape, covering the vast, sandy dunes in a sheet of solid, frozen gas. But when spring arrives, something peculiar happens. On the sunward slopes of these dunes, dark, splotchy spots begin to appear, often surrounded by a surprisingly bright, almost luminous halo. These are the dark dune spots, and they look for all the world like some kind of alien mold slowly spreading across the icy surface. Their formation is a perfect example of Martian physics in action, a process that combines the familiar concept of a greenhouse with the alien behavior of dry ice. The story begins in the deep cold of Martian winter, when temperatures plunge so low that carbon dioxide from the atmosphere freezes directly onto the surface, creating a layer of dry ice. In many places, this frost is opaque and dusty, but on the pristine slopes of sand dunes, it can form a remarkably clear, translucent slab. This transparent ice is the key to the entire mystery. When the weak spring sun rises, its light doesn't just reflect off this icy surface. It passes directly through the clear slab of dry ice, much like sunlight streaming through a glass window. This is the greenhouse effect in its most basic form. The sunlight hits the dark, sun-absorbing sand trapped beneath the ice, warming it up. Now, here's where the Martian magic happens. The sand warms up, but the dry ice above it remains incredibly cold. The warm sand then begins to heat the bottom of the ice slab, causing the solid carbon dioxide to sublimate, turning directly from a solid into a gas. This isn't a slow melt, it's an instantaneous transformation that creates a tremendous pressure buildup right at the boundary between the sand and the ice. The trapped gas needs to escape, and it does so with explosive force. It finds or creates weak points in the overlying ice, and it erupts outward in a jet, carrying with it a fountain of the dark basal sand and dust. This explosive geyser of gas and material is what creates the dark dune spot itself. The ejected dark sand falls back down on top of the clean, bright ice, creating the distinct dark splotch. But what about the mysterious bright halo that often surrounds it? That's a result of the cleaning action of the eruption. The force of the gas jet blowing outwards is so strong that it actually scours away the overlying layer of fine, bright dust that had settled on the ice, revealing the cleaner, brighter ice layer underneath. So we end up with a perfect natural artwork, a central dark spot of deposited sand, surrounded by a bright ring of cleaned ice, all on a canvas of translucent frozen carbon dioxide. This process is uniquely Martian because it relies on the specific properties of carbon dioxide ice and the thin Martian atmosphere. On Earth, our seasonal frost is made of water ice, which melts into liquid water. This liquid then percolates into the ground or runs off. It doesn't trap gas and create explosive vents. The dark dune spots are therefore a direct signature of a carbon dioxide-based climate cycle. They are a dynamic, seasonal reminder that even the most basic physical processes can manifest in utterly alien ways on another world. The precision of these features also tells scientists a great deal about the current conditions. The fact that they form specifically on sunward slopes confirms the greenhouse heating mechanism. Their size and distribution can give clues about the thickness of the ice slab and the wind patterns that deposited the original dust. They are, in effect, natural laboratories, demonstrating a beautiful and violent dance between sunlight, ice, and sand that plays out across the dunes of Mars every single year. This brings us to a mystery that strikes at the very heart of our understanding of the ancient Martian climate, a geochemical conundrum that has forced scientists to completely rethink their models. It's the case of the missing carbonate rocks. On Earth, the story of water and air is written in limestone. Vast shelves of carbonate minerals form in our oceans when carbon dioxide from the atmosphere dissolves in the water and reacts with calcium and magnesium, precipitating out to form layers of rock that can last for billions of years. We have every reason to believe a similar process should have occurred on a wet, early Mars. Our rovers have found definitive proof that water was once abundant, flowing in rivers and standing in lakes. Our orbiters have mapped vast clay-rich regions, another signature of water-altered rock. The logic seemed unassailable. Persistent liquid water plus a carbon dioxide-rich atmosphere should equal widespread carbonate deposits. Yet, when we point our most sophisticated orbital spectrometers at the Martian surface, searching for the distinctive chemical fingerprint of these minerals, we find almost nothing. The carbonates are stunningly rare, appearing only in a few isolated and small deposits. This isn't just a minor discrepancy. It's a fundamental paradox that challenges the entire narrative of a warm, wet, and potentially habitable early Mars. Scientists have been grappling with this puzzle for decades, and several compelling theories have emerged to explain the Great Carbonate Disappearance. The first and perhaps most influential theory suggests that the problem wasn't the water, but its chemistry. The early water on Mars may have been profoundly acidic. We have strong evidence for this from the Opportunity rover's exploration of Meridiani Planum, where it discovered the mineral jarosite, which only forms in highly acidic sulfuric acid-rich waters. In such a harsh, briny environment, carbonate minerals simply cannot stabilize. They would dissolve almost as quickly as they tried to form. Think of it like trying to build a sandcastle with vinegar instead of water. The acidic conditions prevent the structure from holding together. This paints a picture of a Mars where bodies of water were more akin to terrestrial acid mine drainage sites than the neutral, life-friendly oceans of early Earth. If this was the dominant condition, then carbonates never had a chance to accumulate in the first place, solving the mystery by suggesting they were stillborn. A second major theory points the finger at the Martian atmosphere itself. It's possible that the early atmosphere never had enough carbon dioxide to begin with. Our models for a warm, wet Mars require a thick CO2 blanket to create a sufficient greenhouse effect to keep water liquid. But what if that thick atmosphere was a fleeting phenomenon, or what if it was made of something else entirely, like methane or sulfur gases? Without a massive reservoir of CO2 dissolved in the planet-wide water system, there would be no raw material to make carbonate rocks on a global scale. This theory suggests that Mars may have had only brief, episodic warm and wet periods, sandwiched between much longer epochs of cold and icy conditions. In this icy highlands scenario, liquid water would have been scarce and transient, never allowing for the long-term, stable chemical conditions needed for extensive carbonate formation that we see in Earth's geological record. Then there is the tantalizing possibility that we are simply looking in the wrong place, or that we cannot see what is right in front of us. The third leading theory proposes that the carbonates aren't missing at all, they are just buried. On Earth, the most extensive carbonate deposits are on the ocean floors, which are later thrust up by tectonic activity. Mars lacks the active plate tectonics that constantly recycle and uplift rocks, so any ancient seafloor carbonates could be hidden deep beneath layers of volcanic basalt and wind-blown dust. Our orbital spectrometers can only see the very top layer of the surface. They are blind to what lies beneath. Furthermore, some carbonates might be present not as thick, pure layers, but as a fine cement mixed in with other sediments, a mixture that would be incredibly difficult to detect remotely. Recent discoveries add weight to this idea. NASA Perseverance rover, currently exploring the Jezero crater delta, has actually identified carbonates in the rocks there. This is a crucial piece of the puzzle, proving that carbonate formation did happen in some specific, localized environments. The key may be that these environments were the exception, not the rule. Perhaps carbonate formation was confined to specific lakes or groundwater systems where the pH was more neutral, while the rest of the planet's waters were indeed too acidic. The search is now on to determine if Jezero's carbonates are a unique oddity or one small sample of a much larger, hidden reservoir. This isn't just an academic debate over rocks. The implications for the potential for ancient life are profound. Carbonate rocks on Earth are famous for preserving some of our oldest and most exquisite fossils. If Mars truly lacked the neutral pH, carbonate-forming environments, it would have been a much more challenging place for life to emerge and, crucially, to leave behind a detectable fossil signature. The mystery of the missing carbonates forces us to confront the possibility that Mars was never the gentle, Earth-like world we sometimes imagine, but a planet that was mostly cold, acidic, and harsh, with only fleeting oases of habitability. It reminds us that the presence of water alone is not a guarantee of an Earth-like planetary story. As our rovers continue to drill into promising rocks and future missions plan to bring samples back to Earth, the answer to this geochemical ghost story may finally be within our grasp, revealing whether the young Mars was a truly welcoming world or a place where the chemistry itself conspired against the very processes we associate with life. Yet again, Mars presented us with an image that felt ripped from a science fiction novel. In May of 2022, a navigation camera on NASA Curiosity rover captured a photograph of a cliff face in the Mount Sharp region, and within it, a feature that seemed impossibly deliberate, a perfectly rectangular, door-like opening set neatly into the rock as if carved by some intelligent hand. The internet, of course, erupted. Here was the ultimate archetype of a threshold, a passageway leading into the unknown, a literal doorway to another world hidden beneath the Martian surface. The human mind instantly filled in the blanks, imagining what could lie beyond a sheltered cavern, an ancient habitat, or even the entrance to a vast subterranean network. It was a moment of pure, unadulterated pareidolia, the same psychological impulse that conjured the face on Mars, but this time with a different, equally powerful symbol. We weren't just seeing a face, we were being invited to step inside. As always, the scientific explanation, while less sensational, is no less fascinating. Geologists quickly pointed out that this doorway is not a door at all. It is a very small, naturally occurring fracture in the bedrock, likely only a few tens of centimeters high. On Mars, where there is no plate tectonics to constantly crumple and rebuild the landscape, the primary forces shaping the cliffs are stress and erosion. The entire region where Curiosity was traveling is composed of sedimentary rock that was deposited in an ancient lakebed billions of years ago. Over eons, the immense weight of overlying layers compressed this material, but it also created built-in stresses within the rock itself. When the overlying material was later stripped away by wind, the bedrock found itself suddenly unburdened. This release of pressure causes the rock to crack and fracture, much like a layer of dried mud cracking as it contracts. The remarkably straight, rectangular shape of this particular fracture is a common result of this stress release process, especially in brittle, fine-grained sedimentary rock. The forces act along natural planes of weakness, creating clean, geometric breaks. What we are seeing is essentially a small, shallow crevice, its interior darkened by shadows, which creates the perfect illusion of depth and a man-made passage. In fact, if you look closely at the surrounding cliff face, you can see other similar vertical fractures. This one just happens to be isolated and captured from an angle that makes it look like a solitary, crafted entryway. The profound lesson of the Martian doorway, however, is not about geology but about us. It underscores a fundamental and relentless aspect of human psychology. Our pattern-seeking brain is an incredible survival tool, but on an alien world, it can become a powerful engine for misinterpretation. We are wired to seek out the familiar in the unfamiliar, to find signal in the noise. This instinct allowed our ancestors to spot a predator hiding in the tall grass or to recognize a potential tool in a piece of flint. When we project this same cognitive toolkit onto the utterly alien and largely empty landscapes of Mars, it naturally latches onto any feature that resembles something from our own built environment. A door is not just a shape, it is a symbol of transition, of opportunity, of secrets waiting to be discovered. It taps directly into our deepest cultural narratives about exploration and discovery. The immediate and passionate public response to the doorway image proves that this desire is not diminished by decades of scientific exploration. If anything, it is amplified. Each new rover image is scrutinized not just by scientists, but by millions of people around the world, all hoping to be the first to spot something that cannot be explained, something that whispers of a shared history or a parallel existence. This recurring cycle of discovery, excitement, and geological explanation is actually a vital and healthy part of our relationship with the Red Planet. The public's fascination drives engagement, funds missions, and inspires the next generation of scientists and engineers. The doorway became a global talking point not because people were ignorant, but because they were hopeful. It represents a beautiful collision between cold, hard data and the warm, human capacity for wonder. The scientific reality that it's a tiny crack in a rock does not invalidate that sense of wonder, it merely redirects it. The true marvel is that we have a robot on another world, able to photograph such fine details in the rock, allowing us to have this very discussion. The real doorway is not the fracture in the Martian cliff. It is the camera lens of the Curiosity rover itself, a portal through which we can all gaze upon and project our dreams onto the dusty surface of our planetary neighbor. These episodes remind us that exploring Mars is a dual journey, one outward into the solar system and another inward, into the workings of our own minds and the timeless desire to find a little bit of home in the vast, cold expanse of space. That initial foray onto the Martian surface, the Viking missions of the 1970s, were designed with one of the most ambitious goals in the history of science, to find definitive proof of life. Their suite of biology experiments were masterpieces of ingenuity, cleverly designed to detect the metabolic processes of any potential Martian microbes. One of these, the labeled release experiment, seemed to deliver a stunning, almost unbelievable result. When a nutrient soup was added to a sample of Martian soil, something in the soil consumed it, releasing gaseous byproducts in a way that perfectly mimicked the behavior of terrestrial microorganisms. For a few exhilarating moments, it looked like we had done it. We had found life on another world, but the celebration was short-lived. The mission had a built-in control, a second test where the soil was first heated to a temperature that would utterly destroy any known living organism. When the experiment was run again with this sterilized sample, it still produced the same result. The breathing of the soil wasn't biological at all, it was chemical. The Martian soil itself was violently reactive, a hyper-oxidizing agent that was ripping apart the organic nutrients all on its own. This was the discovery of one of Mars's most pervasive and hostile environmental features, a soil so aggressive it can destroy the very building blocks of life. The implications were devastating for the immediate search for life, but it opened up a profound new mystery. what could possibly make the soil of an entire planet act like a powerful bleach? The leading theory for decades has pointed an accusatory finger at the relentless barrage of ultraviolet radiation from the sun. Mars, unlike Earth, lacks a protective ozone layer, so this high-energy light strikes the surface unimpeded. Scientists propose that this UV radiation could be energizing the thin Martian atmosphere and the minerals in the soil, driving chemical reactions that create highly reactive oxidants like hydrogen peroxide. You might have a bottle of this substance in your medicine cabinet as a mild antiseptic. On Mars, it would be produced naturally and in abundance, effectively turning the top layer of the entire planet into a kind of self-sterilizing blanket. This would explain the Viking results beautifully. The soil wasn't alive, it was just saturated with these peroxides, which rapidly broke down the organic compounds in the nutrient solution, creating the false positive. The process would be continuous and global, a natural planet-wide decontamination cycle. However, more recent discoveries from later missions, particularly NASA Phoenix lander, have dramatically refined and complicated this picture. Phoenix, which touched down in the northern Arctic plains, performed a simple but revolutionary test. It scooped up some soil, mixed it with water from Earth in a tiny beaker, and inserted a suite of sensors. The results were startling. The sensors detected the presence of a class of chemicals known as perchlorates. These are salts containing chlorine and oxygen, and they are extraordinarily powerful oxidizers. Their discovery was a game changer. While UV radiation likely still plays a role in their formation and replenishment, perchlorates are now seen as the primary agent behind the soil's reactive nature. They are stable, they can persist in the soil for eons, and they become explosively reactive when wet. This last part is crucial. In the dry, frozen state, perchlorates are relatively benign. But the moment liquid water is introduced, exactly as the Viking life detection experiments did, they spring into action, aggressively tearing apart organic molecules. This explained not only the Viking results with terrifying elegance, but also posed a new and formidable challenge for the search for life. If any ancient or modern microbes existed on Mars, their organic remains would be utterly shredded by this chemical menace, leaving almost no trace for our rovers to find. The presence of perchlorates transforms our understanding of Martian habitability. On one hand, they represent a profound obstacle. They create a surface environment that is actively destructive to complex organic chemistry, effectively erasing the very biosignatures we are desperately searching for. It's as if Mars has a built-in sanitizing system that scrubs away the evidence. This doesn't just affect the search for life, it has direct implications for future human explorers. Perchlorates are toxic to humans, potentially causing serious thyroid problems. Martian dust, which would be fine and pervasive, would be a significant health hazard, requiring rigorous decontamination procedures for any astronauts and their equipment. Yet, in a strange and paradoxical twist, perchlorates also offer a glimmer of hope. Some extremophile microbes on Earth have been found that can actually use perchlorates as a source of energy. For these organisms, the very poison that kills others becomes their food. This raises the tantalizing possibility that if life did ever gain a foothold on Mars, it might have adapted to not just tolerate, but to metabolize these perchlorates, potentially surviving in a subsurface niche where they are present. Furthermore, while perchlorates are devastating for preserving organic molecules on the surface, they can act as a powerful antifreeze, drastically lowering the freezing point of water and allowing for the existence of stable, liquid brines in the shallow subsurface. So, the same chemical that destroys the evidence of surface life might be creating habitable pockets for life to exist just out of reach. The oxidizing soil of Mars is therefore not a simple no to the question of life, but a complex and demanding maybe. A harsh environmental filter that forces any potential biology to be as rugged and resourceful as the planet itself. But while the strange chemistry of the soil presents a formidable barrier, The Martian surface itself is in a constant, dynamic state of renewal and revelation, orchestrated by the planet's thin but active atmosphere. As we look down from orbit upon countless craters, we notice something peculiar decorating their slopes, a stunning gallery of dark and light streaks, painting the terrain with an artist's precision. These are not the seasonal, damp-looking flows of the recurring slope lineae. They are something both more common and, in their own way, just as puzzling. They appear as sharp, slender lines, often starting at a rocky outcrop near a crater's rim and streaming directly downhill, sometimes for kilometers, like delicate strokes of a charcoal pencil on a canvas of rust. Some are dark, some are surprisingly bright, and their stark contrast against the background makes them stand out with breathtaking clarity. They are the signature of the Martian wind, but the specific recipe that creates such perfect, recurring patterns is a mystery of physics and geology that we are only beginning to appreciate. The formation of these streaks is a story of subtraction and addition, a tale of two different processes working in concert. The dark streaks are the most straightforward to understand in principle. They are essentially nature's etch-a-sketch, where the bright, reddish dust that uniformly coats so much of Mars is selectively scrubbed away. The primary artists responsible for this cleaning are dust devils, those swirling, mini tornadoes that dance across the plains. As a dust devil marches up a crater slope, its vortex acts like a giant, natural vacuum cleaner. The low pressure at its core and the strong winds within are powerful enough to lift the fine, bright dust particles from the surface. But this isn't a random scrubbing, it's remarkably precise. The process reveals the darker, underlying substrate beneath. This could be coarse, basaltic sand or older, volcanic rock that hasn't been stained by the pervasive dust. The result is a sharp, dark trail exactly tracing the path of the dust devil as it moved downhill. We have incredible photographic proof of this from orbiters like HiRISE, which has captured dust devils in the very act of creating these streaks, with the dark line appearing directly behind the moving vortex. It's a real-time demonstration of one of the planet's most active surface-shaping processes. The bright streaks, however, present a more counterintuitive puzzle. If dark streaks are formed by the removal of dust, then logic suggests bright streaks must be formed by its deposition. Yet this is where the mystery deepens. How does the wind, which is generally an agent of erosion, manage to deposit material so neatly and consistently in such defined lines? The prevailing theory is that these bright features are actually formed in the lee, or the sheltered downwind side, of small obstacles like boulders or rock ledges. As the wind flows over the crater slope, it hits these obstacles and creates a small wind shadow behind them, a zone of slower, more turbulent airflow. The heavier, brighter dust grains being carried by the wind can't stay suspended in this comma zone, so they fall out of the air and settle there, painting a bright line directly behind the obstacle. Over time, as winds blow consistently from the same direction season after season, these deposits build up, creating the prominent bright streaks we see. This explanation seems elegant, but it begs a deeper question about the nature of the Martian environment. What specific wind patterns and dust properties are required to create such incredibly sharp and persistent features? The real enigma lies in the perfection of these streaks. They are not fuzzy, blurred smudges. They are often knife-edge sharp, maintaining their narrow width over incredible distances. This tells us that the wind patterns on these crater slopes are not chaotic, but remarkably organized and channeled. The shape of the crater itself acts as a giant wind tunnel, funneling air currents in very specific paths. Furthermore, the dust involved must have very particular physical properties. The grains that form the bright streaks must be just the right size and weight fine enough to be lifted and carried by the wind, but coarse enough to fall out of suspension predictably when the wind slows. The dark substrate, once revealed, must also be resistant to being quickly recovered, suggesting that the darker sand grains are heavier or that the area is subject to consistent, cleansing winds that prevent new dust from settling. This creates a delicate, dynamic balance. A single, powerful gust from an unusual direction could theoretically erase or distort these streaks, yet they recur in the same places year after year. This persistence implies a level of meteorological predictability on Mars that is astonishing. The planet's atmosphere, though thin, seems to have its own set of steadfast rules, creating these artistic features with the reliability of a seasonal clock. The streaked craters are therefore more than just a beautiful spectacle. They are a natural laboratory for studying aeolian or wind-driven processes. By analyzing their direction, length, and darkness, scientists can effectively map the wind currents on a scale too fine for our global climate models to capture. They are living, changing diagrams of the Martian atmosphere's intimate dance with the soil, a silent and elegant testament to the forces that continue to sculpt the face of the red planet today. Among the most charming and initially baffling little mysteries of the Mars rover missions was the case of the jelly donut rock. In early 2014, the Opportunity rover was conducting its routine survey of the rim of Endeavour crater when mission controllers received a new set of photographs. As they compared a recent image with one taken just 12 Martian days earlier, they were stunned to see a rock that had absolutely not been there before. It was about the size of a donut with a dark, reddish center surrounded by a bright white rim. It seemed to have just materialized. The team, half jokingly and half in genuine astonishment, dubbed it Pinnacle Island. The immediate, tantalizing question was obvious. How did this rock suddenly appear in a place the rover had already photographed and found empty? For a brief, exhilarating moment, the possibilities seemed wide open. Had it been ejected by a nearby meteorite impact, a rare and precious chance to sample fresh material from beneath the surface? Could some kind of localized geological process, like a small mud volcano or a gas vent, have pushed it up from below? The internet, of course, buzzed with more speculative ideas, but the true explanation, once the rover team had time to analyze the imagery and the context more carefully, was far more straightforward and in its own way just as instructive. Opportunity's own wheel had done it. By maneuvering around the site, the rover had inadvertently driven over a larger, partially buried rock just a few feet away. The wheel's traction cleats had snagged this smaller jelly donut rock, which was actually just a broken-off piece of that larger stone, and flipped it right into the rover's field of view. The white-rimmed appearance was simply the freshly exposed interior of the rock, which had been protected from the oxidizing Martian environment, while the darker exterior was the weathered, dust-coated surface. It was a classic case of a rover creating its own mystery, then solving it with a little detective work. This whimsical episode serves as a perfect, real-world parable for the challenges of exploring an active world, even one as seemingly still as Mars. It highlights a crucial point: the Martian surface is not a static museum exhibit. It is a dynamic environment where changes are constantly occurring, and not all of them are of natural, planetary origin. Our own robotic explorers are active agents on the landscape. Their wheels churn up the soil, break apart fragile rocks, and leave behind distinctive tracks that can themselves become subjects of study. When we see something new, we must first ask a very practical question: could we have caused this ourselves? The jelly donut rock was a benign example, but it underscores the rigorous process of elimination that planetary scientists must follow. Every anomaly is treated with initial excitement, but then subjected to a meticulous forensic analysis. They examine the before and after images from multiple angles. They look for wheel tracks leading to the object, and they analyze the chemistry of the new find compared to its suspected source rock. This process of self-critical inquiry is the bedrock of good science, ensuring that we don't mistake our own footprints for the footprints of an alien. Yet, this self-awareness also sharpens our ability to recognize the truly natural and fascinating changes that occur without our intervention. The fact that we can so clearly see the mark of a rover wheel means we are also perfectly equipped to observe the marks left by Martian weather. The same high-resolution cameras that caught the jelly donut in its new location are constantly documenting the work of the wind. We see new dust devil tracks appearing between orbital passes, watching as these whirlwinds act as planetary cleaning service, scouring bright dust away to reveal darker substrates. We observe small avalanches of sand on dune slopes, triggered by the seasonal thawing of carbon dioxide frost. In the polar regions, we've even witnessed the sudden appearance of new impact craters, formed by meteorites that slammed into the surface and blasted away the overlying dust, exposing the fresh ice beneath. The jelly donut incident, therefore, teaches a dual lesson. It makes us more humble interpreters of the Martian landscape, reminding us that we are not passive observers but participants who leave a trace. At the same time, it calibrates our instruments, both technological and intellectual, allowing us to better distinguish between the mundane, the human-caused, and the genuinely extraordinary. It is a reminder that on Mars, even the simplest explanation can lead to a deeper appreciation of the complex and ever-changing world we are so privileged to explore. This brings us to a question that stands as one of the grandest in all of planetary science, a problem that pits the clear and obvious evidence of a watery past against the harsh, unforgiving physics of the present. We call it the low-gravity paradox. Look at the river deltas photographed by the Curiosity rover, their intricate, branching patterns unmistakably formed by persistent flowing water. Consider the immense canyons like the 1,000-kilometer long scar of Casey Valley that looks like it was carved by a flood of almost biblical proportions. The evidence that liquid water once flowed freely on Mars is etched into its surface as clearly as words on a page. Yet when we look at Mars today, a frozen desert with an atmosphere 100 times thinner than Earth's, the physics simply doesn't add up. With such low gravity and such a thin blanket of air, liquid water cannot survive on the surface. It would either instantly boil away in the low pressure or rapidly freeze in the sub-zero cold. So how, then, did these vast, long-lived river systems and deep, standing lakes ever exist? This is the central, baffling contradiction. The geology demands a warm, wet world, but the basic properties of the planet seem to make that an impossibility. Unraveling this paradox forces us to rewind the clock billions of years and imagine a Mars that was almost unrecognizable from the world we see today. The most widely accepted solution points to a lost golden age, a time when Mars was wrapped in a much thicker, protective atmosphere. Think of this ancient atmosphere as a planetary overcoat. A dense shroud of gases, primarily carbon dioxide, would have created a powerful greenhouse effect, trapping the sun's heat and raising global average temperatures above the freezing point of water. It would have also provided the necessary surface pressure to keep water in its liquid state, preventing it from instantly vaporizing. But this immediately raises another, even more difficult question. Where did that thick atmosphere go? A planet can't just misplace an entire sky. The leading suspect in this planetary whodunit is the Sun itself, acting in concert with Mars's own internal workings. Billions of years ago, Mars is thought to have had a global magnetic field, much like Earth's today, generated by a churning, molten metal core. This magnetic field would have acted as an invisible shield, deflecting the constant stream of charged particles from the Sun known as the solar wind. Without this shield, the solar wind strikes the upper atmosphere directly, and over millions of years, it has the power to strip it away, molecule by molecule, blasting it off into space. The prevailing theory is that when Mars's core cooled and solidified, its magnetic dynamo shut down. Once that protective shield fell, the solar wind began its slow, relentless work of scouring the atmosphere away, leaving behind the wispy, defenseless envelope we see today. Our orbiters have even detected this process in action, measuring ions of atmospheric gas being dragged out into the void by the solar wind, a silent, ongoing theft that began eons ago. However, this elegant story of a single catastrophic shutdown is now facing serious challenges, leading to a vibrant and ongoing scientific debate. The timeline just doesn't seem to fit neatly. Evidence from Martian meteorites and surface geology suggests that the magnetic field died very early in the planet's history, perhaps within the first 500 million years. Yet, we have clear evidence from lakebed sediments explored by rovers like Curiosity that large bodies of water persisted on the surface for perhaps 1 billion years or more after the magnetic field was gone. How could a warm, wet climate have survived for so long without its protective magnetic shield? This discrepancy has forced scientists to propose alternative and sometimes overlapping explanations. One compelling idea is that the early atmosphere was just so incredibly thick that even after the magnetic field vanished, it took the solar wind hundreds of millions of years to strip it down to its current state. It was a battle of attrition, with Mars starting with such an immense atmospheric reserve that it could withstand the bleeding for a very long time. Another theory suggests that the loss wasn't a steady trickle but a series of catastrophic, punctuated events. Perhaps massive asteroid impacts, which were common in the early solar system, could have blasted huge portions of the atmosphere into space in single, violent blows. Alternatively, the chemistry of the atmosphere itself might have provided a temporary buffer. If the early atmosphere was rich in hydrogen, a lightweight gas that escapes more easily, its initial loss could have dragged away other, heavier gases, accelerating the process in a dramatic early collapse. The paradox deepens when we consider the specific requirements for the water features we see. Some of the ancient river channels are extraordinarily long, implying they were fed by rainfall or snowmelt over thousands of years, not just a brief, chaotic gush. This suggests a climate that was not just temporarily warm but stable. To achieve this, some climate modelers have proposed that the atmosphere couldn't have been made of carbon dioxide alone, as CO2 eventually condenses into clouds or forms carbonate rocks when in contact with water. They suggest other, more potent greenhouse gases like methane or sulfur hexafluoride must have been in the mix to provide the sustained warming needed. Others point to the planet's extreme axial tilt. Mars's tilt wobbles dramatically over time, far more than Earth's. During periods of high obliquity, the poles would point directly at the sun, causing the polar ice caps to sublimate and release their stored water and carbon dioxide into the atmosphere, creating short, intense, interglacial periods of warmth and runoff that could have carved the valleys we see. In this scenario, Mars wasn't consistently warm and wet like a tropical Earth, but was mostly cold and icy, punctuated by brief, dramatic thaws. This icy highlands hypothesis reframes the paradox entirely, suggesting the water was mostly locked in ice and the flowing rivers were a transient, seasonal phenomenon, not a permanent feature of a balmy world. The low-gravity paradox, therefore, is far from solved. It pushes us to move beyond a simple, single-cause explanation and to consider a complex interplay of geology, astronomy, and atmospheric chemistry, a story of a planet that may have taken many different paths to its current frozen state, each leaving its own mysterious watermark on the surface for us to decipher. Buried within the dusty, ancient lakebed of Gale Crater, the Curiosity rover has been performing a kind of high-stakes chemistry, drilling into billion-year-old mudstone and heating the samples in its onboard laboratory. The data it sends back contains what might be the most tantalizing and frustrating clues in the entire search for life's precursors, the faint but definitive whispers of organic molecules. These are not proof of life, not by a long shot, but they are the essential building blocks from which all known life is constructed. Finding them on Mars is like walking into a vast, abandoned workshop and discovering that, while the workers are gone, the raw materials, the lumber, the nails, the glass are still scattered everywhere. It confirms that Mars possessed the fundamental chemical ingredients for life to potentially get started. The types of molecules detected are particularly telling. Curiosity has identified a variety of thiophenes, aromatic compounds like benzene, and even small chains of carbon atoms. On Earth, such molecules can be the broken-down remnants of ancient, decayed microorganisms. But, and this is the critical twist, they can also be synthesized through completely non-biological means. Meteorites constantly rain down organic material from space, and chemical reactions driven by geothermal heat or even the simple interaction of water and rock can forge these carbon-based compounds without any need for a living cell. The central challenge, therefore, is not just finding the organics but reading their story. Were these molecules simply part of the non-living chemical inventory of early Mars, delivered by comets or forged in its rocks? Or are they the fossilized chemical echoes of something that was once alive? To unravel this mystery, scientists act as cosmic detectives, looking not just at what the molecules are, but at their context and their companions. One of the most significant clues came from a 3-billion-year-old mudstone sample nicknamed Mojave 2. When Curiosity analyzed it, it found a fascinating correlation. A spike in organic molecules coincided with a spike in the element manganese. On Earth, manganese is often concentrated by microbial activity or by the presence of oxygen in water. This association doesn't prove life was involved, but it paints a more specific picture of the ancient environment in that particular spot of Gale crater. It suggests the lake was not only present but may have been chemically stratified, with oxygen-rich waters that could facilitate the complex chemistry needed to form and preserve these organics. It moves the story from a simple organics are present to a more nuanced organics are present in an environment that was plausibly habitable. Another layer of intrigue comes from the isotopic composition of the carbon within these molecules. Isotopes are different forms of the same element that have varying atomic weights. Life on Earth has a marked preference for the lighter carbon-12 isotope over the heavier carbon-13, as it requires less energy to incorporate into cellular structures. If future missions or the samples brought back to Earth were to find a similar light carbon signature in the Martian organics, it would be a powerful, though still not conclusive, indicator of biological processing. It would be a signature that strongly hints a living organism was making choices, however microscopic, about its chemical diet. The persistence of these organics for billions of years is itself a minor miracle, given the hostile, oxidizing nature of the Martian soil. Their survival suggests they were protected, perhaps buried quickly by sediment in the bottom of a lake, sealed away from the destructive radiation and chemical agents at the surface. This makes the specific location of Gale crater so important. It was an environment with a strong potential to not only create the conditions for life, but also to preserve its evidence. The whispers we are hearing are faint because they have been filtered through eons of geological time and planetary change. They are not a shout of "we are here," but a murmur from a once wet world saying, "the possibility was here." Each new detection refines our search, telling us that while we have not found life, we are looking in the right places, examining the right rocks, and asking the right questions. The journey to understand these organic whispers is a slow, meticulous process of elimination, ruling out non-biological origins one by one, inching us closer to the day when we might finally hear a signal that is unmistakably and definitively alive. Orbiting just a few thousand kilometers above the rusty plains are two of the most peculiar companions in the solar system, the moons of Mars, Phobos and Deimos. Unlike our own stately, spherical moon, these two objects are misshapen, cratered, and tiny, looking more like lumpy potatoes than proper worlds. Phobos, the larger of the two, is only about 27 kilometers across at its widest point, while Deimos is a mere 15. They are so small and their gravity so weak that an astronaut standing on their surface could, with a good running start, throw a rock clear off into space. Their appearance and composition, as measured by spectral data, scream asteroid. They are dark, carbon-rich bodies, strikingly similar to the kind of asteroids found in the outer reaches of the main asteroid belt. This has led to the long-standing and most intuitive theory that these moons are not native to Mars, but were instead captured by its gravity long ago. Two wayward wanderers snared from the vast population of space rocks that drift between the planets. Yet the capture theory, while elegant, runs into a formidable problem when you examine their paths around Mars. The orbits of Phobos and Deimos are almost perfectly circular and lie neatly along the planet's equatorial plane. This is highly unusual for a captured object. When a planet gravitationally captures a passing asteroid, the resulting orbit is typically a wildly elongated, tilted ellipse. For the orbits to become so circular and so well aligned, some other mechanism would have had to smooth them out over time, like atmospheric drag or tidal forces, but the evidence for that is shaky at best. This orbital neatness is the first major clue that the classic capture story might be wrong. The plot thickens considerably when we look at the dynamic future of the inner moon, Phobos. It is in a slow, inescapable death spiral, orbiting closer to its planet than any other moon in the solar system. Phobos is relentlessly feeling the tug of Martian gravity. The moon's gravity creates a tidal bulge on Mars, but because Mars rotates faster than Phobos orbits, this bulge actually pulls ahead of the moon, acting like a constant gravitational brake. This tidal interaction is siphoning energy from Phobos's orbit, causing it to creep steadily inward by about 2 centimeters every year. In about 50 million years, it will cross a treacherous boundary known as the Roche limit. At that point, the difference in gravity between the side of Phobos facing Mars and the side facing away will become stronger than the forces holding the moon itself together. Phobos will be torn asunder, shattered into a million pieces, and Mars will, for a time, sport a brilliant, disintegrating ring of rubble. The impending doom of Phobos adds a dramatic, ticking clock element to its mystery. This orbital behavior and the problem of their neat paths have given rise to a compelling and increasingly popular alternative, the giant impact hypothesis. This theory paints a spectacular picture of the early solar system, a time of colossal violence. Imagine a protoplanet, perhaps the size of Ceres, smashing into a young Mars. The impact would have been cataclysmic, blasting a huge cloud of vaporized rock and debris into space, a cloud that would have been predominantly Martian in composition. Much of this material would have rained back down on the planet, but some of it would have been flung into orbit where it could have coalesced under its own gravity to form a moon. This is in fact the leading theory for the formation of our own Earth's moon. In the case of Mars, a single large moon could have formed from the debris disk. But then, how do you get two small, asteroid-like moons instead of one large one? The theory proposes that this larger parent moon had its orbit gradually altered by tidal interactions, much like Phobos is experiencing today. As it spiraled outward, it would have crossed orbital resonances that pumped energy into it, causing it to be pulled apart. The debris from this shattered moon then reaccreted into the two smaller, lumpy bodies we see today, Phobos and Deimos. This would explain their equatorial orbits. They formed from a disk of debris circling Mars's equator and their peculiar composition. Their dark, carbon-rich appearance wouldn't be because they are captured asteroids, but because they are made of the bruised and battered outer layer of that original moon, a layer that was heavily altered by the intense heat of the impact and subsequent exposure to space for billions of years. The debate between the capture and impact origins is far from settled, and it's a debate that future missions hope to resolve. the Japanese space agency JAXA is planning the Martian Moon's e-exploration, or MMX, mission, which aims to land on Phobos, collect samples, and return them to Earth. The composition of those samples will be the ultimate arbiter. If Phobos is truly a captured asteroid from the outer asteroid belt, its sample will look very different from the basaltic rocks we know make up the surface of Mars. If, however, it is made of material that matches the Martian crust but has been processed and altered by eons in space, the giant impact theory will gain immense credibility. The synchronous moons of Mars are therefore not just orbital curiosities. They are the potential leftover children of a planetary catastrophe, holding within their fractured structures the story of a violent impact that may have shaped the red planet's earliest history. Their silent, looping dance is a physical question, one that we are now reaching out to answer, hoping to learn whether they are adopted orphans from the asteroid belt or the true, shattered progeny of Mars itself. But beyond the dust and the rocks, Mars possesses an atmosphere with its own set of quiet, ethereal phenomena, painting the night sky with a light we cannot see with our own eyes. High above the surface, where the thin Martian air meets the void of space, the Methane orbiter has detected a persistent, ghostly emission, a faint but distinct green and ultraviolet glow that illuminates the darkness. This is not the shimmering curtain of an aurora, sparked by solar particles slamming into the poles, but something far more widespread and constant, a night glow. On Earth, we have a similar, though much weaker, air glow, a faint luminescence that is the atmosphere's own built-in light source, a product of chemistry played out on a planetary scale. The process begins during the day, when the sun's intense ultraviolet radiation blasts apart molecules in the upper atmosphere, specifically carbon dioxide and nitrogen. This creates a soup of individual atoms and simple molecules, which are then carried by high-altitude winds. As night falls and these winds transport their chemical cargo to the night side of the planet, the atoms begin to descend into denser layers of the atmosphere. There, in the cold darkness, they slowly recombine. It is this act of recombination, of two oxygen atoms coming together to form a single oxygen molecule, that releases a tiny packet of energy in the form of light, creating the soft greenish glow that Methane observed. Think of it as the atmosphere slowly, quietly sighing out the energy it absorbed during the day, a gentle afterglow of solar radiation. The Martian night glow, however, is far more than just a pretty light show. It is a direct window into the invisible machinations of the planet's atmosphere. The specific patterns and intensities of this glow are profoundly different from what we see on Earth, and these differences are crucial clues. On our planet, air glow is relatively uniform, a diffuse veil across the sky. On Mars, the glow is concentrated in specific, shifting patches, and it is surprisingly bright. This tells scientists that the atmospheric circulation on Mars is much more turbulent and tightly organized than previously assumed. The glow acts like a tracer, a luminous dye injected into a river of air, allowing us to map the complex wind currents that flow from the day side to the night side. The brightness of the glow indicates the speed and efficiency of this process. It reveals that atoms are being funneled from the sunlit hemisphere to the dark one with remarkable vigor, creating concentrated zones where recombination happens rapidly and intensely. This isn't a gentle, global breeze. It's a focused, high-speed atmospheric conveyor belt, and the night glow is its glowing signature. Furthermore, the detection of a simultaneous ultraviolet glow adds another layer of diagnostic power. This UV emission comes from nitric oxide, a molecule that forms when nitrogen and oxygen atoms collide. The presence and strength of this ultraviolet component provide a separate, independent measurement of the atmospheric dynamics at a slightly different altitude. By observing both the green and the UV glow together, scientists can build a three-dimensional picture of how different layers of the atmosphere interact and mix during the Martian night. This data is vital because it helps solve one of the lingering puzzles of the Martian climate: how the upper and lower atmospheres exchange energy and material. The night glow reveals that this exchange is vigorous and structured, driven by global-scale waves and tides that pulse through the thin air, shaping the planet's climate in ways our models are only beginning to capture. This eerie, invisible light show, therefore, is a powerful tool. It allows us to see the wind itself, not by watching dust move, but by observing the very chemistry of the air as it is sculpted by forces we would otherwise be blind to, proving that even in the profound darkness of a Martian night, the atmosphere is never truly at rest. But perhaps no rover has encountered a landscape more visually arresting than the one Curiosity has been slowly climbing for years: the lower slopes of Mount Sharp, the immense central peak that rises from the heart of Gale Crater. Here, the terrain takes on an almost mythical quality, resembling the hide of a colossal, slumbering beast. Vast sections of the mountainside are covered in a pattern of interlocking, plate-like scales, a texture so pronounced and so alien that it's been nicknamed the dragon scales of Mars. These are not small features. Individual scales can be the size of dinner plates or even larger, creating a sweeping, reptilian skin that stretches across the rust-colored slopes. This is not a case of pareidolia or a trick of the light. These are real, physical textures etched into the bedrock itself, the result of one of the most fundamental and powerful forces in the universe: time. The dragon scales are a spectacular example of differential erosion, a process where some layers of rock are harder and more resistant than others. As the relentless Martian wind, a sandblaster operating for billions of years, scours the mountainside, it chews through the softer layers much faster than the harder ones. The result is a landscape that looks like it has been carved with a chisel, where the tougher, more resilient rock stands proud, forming these raised, scale-like plates, while the softer material has been scooped out from between them. This much we understand. The true mystery, the question that geologists are piecing together with every drill sample and high-resolution image, is what specific ancient environment created rock with such a bizarrely variable and durable personality in the first place. To solve this, we have to read the mountain like a book, and each of these scales is a word in a billion-year-old story. Mount Sharp itself is not a volcano like Olympus Mons. It is a gigantic stack of sedimentary layers, the accumulated dirt, sand, and silt that slowly settled at the bottom of the ancient lake that once filled Gale Crater. The dragon scales represent a specific chapter in that depositional history, a period where the environment was shifting in a dramatic and cyclical way. One compelling theory is that we are looking at the fossilized remnants of ancient wind-blown dunes. Imagine a time long after the lake in Gale Crater had partially dried up, when powerful Martian winds whipped across the landscape, piling up vast fields of sand. These dunes would have been massive, and as they migrated, they left behind distinct, cross-bedded layers in the rock record. The scaly texture could be the exposed cross-sections of these petrified dune fronts. The variation in hardness between the scale and the recessed area could be due to differences in how the sand grains were sorted and cemented together by minerals carried in groundwater long after the dunes were buried. Coarser, well-sorted sand grains from the heart of the dune might have formed a tougher layer, while finer, dustier sediment deposited in the dune's slip face or between dunes could have created a softer, more easily eroded layer. A second, equally plausible hypothesis points directly to the lake itself. Gale Crater was not a static bathtub. Its water levels rose and fell dramatically over millions of years. The dragon scales could be the signature of these fluctuating shorelines. In this scenario, each scale represents a layer of sediment deposited during a different climatic phase. A durable scale might be a layer of chemical precipitates like the evaporites left behind when a body of water dries up and minerals like gypsum or hematite crystallize out, forming a very hard, resistant layer. The softer material in between could then be a layer of fine, loose mud or silt that settled in deeper, quieter waters when the lake was full. The entire pattern would then be a record of the lake's pulse, a rhythmic rising and falling that built up a stack of layers with wildly different abilities to withstand the eroding wind. What makes the puzzle so fascinating is that these two stories, the windy desert and the pulsing lake, are not mutually exclusive. The real history of Mount Sharp is almost certainly a complex interplay of both. The climate of ancient Mars was likely not stable. It probably swung between wet, lake-forming periods and dry, desert-like eras. The dragon scales could therefore be a hybrid formation, a layer cake where episodes of dune formation were interrupted by sudden inundations from a returning lake, which then deposited a layer of mud on top of the sand, only for the climate to dry out again and for new dunes to march across the muddy lakebed. This cycle, repeated over and over, would create the perfect recipe for differential erosion. Each shift in environment would deposit sediment with a different grain size, mineral composition, and porosity, leading to the patchwork of hard and soft layers that defines the scaly terrain today. Every time curiosity drills into one of these scales, it's not just sampling rock. It's conducting a forensic investigation into the planetary climate of a lost world. The data it sends back helps scientists determine the precise grain size and mineralogy, allowing them to distinguish between a rock that formed in a fast-moving stream, a quiet lake, or a windswept dune field. The dragon scales, in their stark and beautiful geometry, are therefore more than just a geological oddity. They are a high-fidelity archive, preserving the intricate stop-and-start story of how a wet Mars transformed into the dry world we see today, one scale at a time. But while the debate over that one possible subglacial lake continues, it has opened our eyes to a much wider and more puzzling reality. The same ground-penetrating radar technology that revealed that initial bright reflection has since been scanning other parts of Mars, and it's finding that the South Pole is not alone. Scattered across the mid-latitudes and even beneath the equatorial regions, orbiter instruments like Marsus and Charad are detecting their own suite of mysterious, bright subsurface reflections. These anomalies are like ghostly echoes from the deep, suggesting that the interior of Mars is far more complex and varied than we ever imagined, a hidden landscape filled with features we are only just beginning to map. The central challenge, and the reason for so much scientific disagreement, lies in the very nature of how this radar works. The instruments send low-frequency radio waves down through the planet's crust, and these waves bounce back when they hit a boundary between different materials. A particularly bright, sharp reflection, what scientists call a high dielectric constant, typically indicates a sudden and dramatic change in the composition of the subsurface. On Earth, the brightest reflections like this almost always come from liquid water because it's an excellent conductor of electricity. That's why the initial interpretation of the South Polar feature as a lake was so compelling. But on Mars, other substances can create a nearly identical signal, turning each new discovery into a fascinating detective story with multiple suspects. One of the leading alternative explanations for these bright reflections is not water, but volcanic rock. Mars is a world built on basalt, the same dark, dense rock that forms the ocean floors on Earth. But volcanic history is messy. There can be layers of volcanic ash or flows of very smooth, dense lava that create a sharp, flat boundary deep underground. When the radar wave hits the top of one of these solid, continuous lava layers, it can bounce back with a strong, bright signal that perfectly mimics the signature of a liquid water layer. The key to distinguishing between the two often lies in the context. If a bright reflector is found in a region we know to be geologically active or volcanically recent, the case for a rock layer becomes much stronger. But Mars's volcanic history is long and complex, and we don't have a complete map of all its subsurface lava tubes and frozen flows, making it entirely plausible that we are mistaking ancient, buried geology for modern-day aquifers. Another compelling possibility involves not rock or water, but frozen carbon dioxide. We know that the polar regions and mid-latitudes have vast reservoirs of water ice mixed with dust, but there could also be deep deposits of dry ice, frozen carbon dioxide, hidden beneath the surface. The electrical properties of solid CO2 are not as well studied in these contexts, but some laboratory experiments suggest that under the right conditions of temperature and purity, a thick layer of dry ice could also produce a very bright radar return. This would be a profoundly different kind of discovery, pointing to a much more dynamic exchange of carbon dioxide between the atmosphere and the subsurface over millions of years, a hidden part of the planet's climate cycle we haven't yet accounted for. Then there is the prospect of unusual, exotic sediment deposits. Imagine a layer of metallic minerals, like the iron oxides that are so common on the surface, but buried and concentrated into a dense, continuous sheet by some ancient geological process. Or consider the possibility of thick, pure layers of clay minerals like smectites, which can contain a lot of water within their mineral structure. This type of water, bound up in the clay itself, is not free-flowing liquid, but it can still be highly conductive and produce a very strong radar echo. This is perhaps the most tricky alternative to rule out because it still involves water, just in a different, more solid state. A bright reflection could therefore represent a massive, deeply buried clay deposit, a fossilized swamp from a wetter era rather than a modern liquid lake. The difficulty is that from orbit with a single type of measurement, all of these different materials, liquid brine, solid lava, pure clay, or frozen CO2, can look frustratingly similar. This fundamental ambiguity is why you will often see conflicting headlines about these discoveries. One research team, focusing on the brightness of the signal and the geological context, might publish a paper strongly arguing for the liquid water interpretation. Almost simultaneously, another team, using a different computer model to simulate how the radar wave interacts with possible materials, will publish a counter-argument showing that clay or volcanic rock is just as likely, if not more so. This isn't a sign of broken science, it's the sound of a vigorous, healthy debate, the rigorous process of testing a thrilling idea against every possible alternative. The way forward is to gather more data and from different angles. Future radar missions might use a wider range of frequencies which can help distinguish between the various candidates. Or a network of landers equipped with seismometers could help us build a clearer picture of the subsurface structure, telling us if these bright reflectors are flat, liquid-like layers, or angled, solid geological formations. Each of these subsurface anomalies, whether it turns out to be a lake, a lava flow, or a layer of clay, is a piece of the puzzle. Together, they are slowly revealing that Mars is not a simple, frozen rock, but a world with a deep and layered history, its most profound secrets hidden just out of sight, waiting for the right key to unlock them. Yet another layer of mystery was added to the Martian atmosphere, not by an orbiter gazing down, but by a single, stationary laboratory sniffing the air in Gale Crater. For 3 Martian years, that's nearly 6 Earth years, the Curiosity rover has been acting as a meticulous atmospheric chemist, using its sample analysis at Mars Instrument to measure the precise composition of the gases around it. It tracked the predictable rise and fall of nitrogen and argon, which behaved exactly as scientists anticipated, ballooning and contracting in concentration as carbon dioxide froze out at the poles each winter and returned to the atmosphere each spring. This seasonal dance of the major gases made perfect sense, but then there was the oxygen. The data revealed that oxygen, which makes up about 0.16% of the Martian atmosphere, did something entirely inexplicable. Throughout the spring and summer, the amount of oxygen in the air would increase by up to 30%, a dramatic surge that peaked just as the planet was at its warmest. Then, in the fall and winter, it would plummet to levels significantly lower than expected. This bizarre cycle repeated each year, but the magnitude of the swing was never exactly the same. No known chemical or physical process could account for this behavior. It was as if the planet was taking a deep, erratic breath, inhaling and exhaling a gas for reasons that remain utterly opaque to us. The discovery sent atmospheric modelers back to their whiteboards, confronting them with a fundamental gap in their understanding of how Mars operates on a seasonal scale. The first and most obvious suspects in any atmospheric mystery are the planet's abundant carbon dioxide and water. The theory was straightforward. When the massive carbon dioxide ice cap at the South Pole sublimates in the spring, it releases a huge volume of gas into the atmosphere. Perhaps, scientists reasoned, this process could also be releasing oxygen trapped within the ice, or the increased sunlight could be breaking apart CO2 or water vapor molecules high in the atmosphere, creating a seasonal pulse of free oxygen. Yet, when they ran the numbers, this entire line of reasoning collapsed. The amount of oxygen being injected into the atmosphere was simply far too great. To produce the observed surge, the processes would need to generate about 10 times more oxygen than these known mechanisms are capable of. Furthermore, the oxygen disappears again far too quickly in the fall. If it were just being mixed into the general atmospheric reservoir, it should linger for much longer. Instead, it vanishes with a speed that suggests something on the surface or in the immediate subsurface is actively and aggressively scrubbing it from the air. This points the investigation away from the sky and directly toward the ground, toward the rusty soil that Curiosity is sitting on. This has led to the primary, though still unproven, hypothesis that the answer lies in the complex and reactive chemistry of the Martian soil itself. We already know the regolith is a powerful oxidizer, filled with perchlorates and other exotic compounds. The thinking is that these soils could be acting like a massive planetary-scale chemical sponge, alternately soaking up oxygen from the air and then releasing it back under specific conditions. The trigger for this cycle could be linked to the intense ultraviolet radiation that bathes the Martian surface. During the sunnier, warmer months, UV light might be providing the energy needed to break down perchlorates or other oxidizing agents in the soil, a process that could slowly release their stored oxygen back into the atmosphere. Then, as conditions cool and darken in the autumn, the chemistry could reverse, with the soil once again becoming a potent sink, pulling oxygen out of the air and locking it away in new chemical bonds. It's a compelling idea, but it's fraught with unanswered questions. Laboratory experiments on Earth have struggled to replicate a chemical cycle that is both efficient enough and fast enough to explain the dramatic 30% swings observed by Curiosity. The specific chemical pathways remain elusive, a frustrating ghost in the machine of Martian soil chemistry. Another fascinating possibility involves water, but in a way we hadn't previously considered. While there isn't enough water vapor in the atmosphere to split apart for the oxygen, there could be significant reservoirs of water ice or very briny liquid water just below the surface. The seasonal temperature changes could be driving a process where this subsurface water interacts with radiation or with specific minerals, producing oxygen gas that then slowly percolates up through the porous soil. The drop in oxygen levels could then be due to that same subsurface environment becoming a chemical sink when temperatures plunge. This theory elegantly ties the oxygen mystery to other subsurface enigmas, like the potential for hidden brines, but it also lacks direct evidence. We simply do not know the extent or the behavior of shallow subsurface water on Mars well enough to confirm or deny its role. The frustrating truth is that we are likely dealing with a chemical process that is completely novel, something that doesn't have a direct analog on Earth because our planet's environment is so different. Mars, with its thin, dry, and radiation-bathed atmosphere, may be conducting a form of chemistry that we are only just beginning to glimpse. The seasonal oxygen fluctuation is therefore more than just a curious data point. It is a direct challenge, a signal that our current models of the Martian environment are still missing a major piece of the puzzle, a piece that could redefine our understanding of the planet's modern-day chemical activity. Yet another celestial mystery is unfolding not on the surface of Mars, but on the tortured face of its innermost moon. Phobos, that lumpy, potato-shaped companion locked in a slow death spiral, is covered in a bizarre and haunting pattern. Across its dusty surface runs a network of parallel grooves, long, linear depressions that look like giant claw marks scraped across the moon's face by some cosmic beast. At first glance, they resemble chains of craters, as if a shotgun blast of debris had strafed the surface in perfectly straight lines. But a closer look reveals something even stranger. These aren't your typical bowl-shaped impact craters. They are often shallower and more elongated, like ditches or troughs, and they run in suspiciously parallel families, crisscrossing the landscape with a geometric precision that nature rarely produces by chance. These are what planetary scientists call hollows, and their origin is one of the most heated debates in Martian system science. The central question is as simple as it is profound. Are we looking at scars from things that hit Phobos, or are we witnessing the moon cracking itself open from the inside out? The traditional explanation for any line of pits on an airless body is a chain of secondary impacts. When a large asteroid slams into a planet like Mars, it can blast millions of tons of debris high into space. Some of this ejected material can fall back in a coordinated, linear rain, scouring a line of craters across the landscape of any nearby moon. This theory certainly has merit. We see similar, though less extensive, crater chains on our own moon, and we know Mars has been bombarded by impacts throughout its history. The grooves on Phobos do seem to radiate outward from Stickney, its massive gash of a crater, which fits the secondary impact model perfectly. However, this neat explanation begins to fray at the edges when you examine the grooves in detail. Some of the most prominent grooves don't actually point directly back to Stickney at all. Their trajectories seem misaligned, suggesting they came from other, unknown impact events. Furthermore, the grooves have some peculiar physical properties. They often have raised rims, and some appear to be filled with a finer, looser material than the surrounding terrain, characteristics that aren't always consistent with a simple impact origin. The sheer number and perfect parallelism of the grooves also seem excessive, as if Phobos was subjected to an impossibly organized and relentless barrage of Martian debris. This is where the more dramatic and perhaps more compelling alternative theory comes into play. This second hypothesis suggests that the grooves are not external scars, but the visible symptoms of profound internal stress. Phobos is in a precarious position. It orbits Mars closer than any other moon in the solar system, and it's getting closer every day, caught in an inescapable gravitational tug of war. The immense tidal forces from Mars are relentlessly pulling on the small moon, because Phobos is not a single, solid chunk of rock, but likely a rubble pile, a loose aggregation of boulders and dust held together by its own meager gravity. It is particularly vulnerable to these strains. The tidal forces are stretching it, and as it orbits, these stresses shift and change, slowly flexing the entire structure. The groove and hollow patterns in this view are essentially stretch marks. They are fractures developing in the moon's outer layer, the regolith, as the whole body is gradually pulled apart. In this scenario, the hollows themselves are formed when this cracked, unconsolidated material is shaken loose by seismic tremors, moonquakes triggered by the tidal stresses, and gently ejected into the space around Phobos, where it either forms a faint, temporary ring or slowly spirals down to crash into Mars. This would explain why the hollows look different from impact craters. They are the result of a slow, gravitational excavation, not a violent, high-speed collision. The difficulty in choosing definitively between these two theories highlights the most fundamental mystery of all. We have no idea what Phobos is like on the inside. Is it a solid, monolithic block which would better withstand tidal forces and lend more credence to the impact theory? Or is it a fragile pile of rubble, a collection of fragments from a long-ago collision, which would be far more susceptible to tidal disruption and make the stress fracture theory much more likely? Our current data is frustratingly ambiguous. The Moon's density is very low, suggesting it is highly porous, which supports the rubble pile model. But we cannot be sure if that porosity is from vast empty caverns inside a solid body or from the gaps between a jumble of loosely packed boulders. This single unknown, the internal structure, is the key that unlocks the mystery of the grooves. Future missions, like the Japanese MMX spacecraft, which aims to land on Phobos and bring samples home, are designed to finally answer this. By analyzing the material from the grooves themselves, scientists will be able to determine its composition. If it matches the unique mineralogy of Martian surface rocks, it would be a strong vote for the secondary impact theory, as it would be literal pieces of Mars that were blasted up and then fell back down on its moon. If, however, the groove material is the same as the rest of Phobos, it would powerfully support the idea that the moon is simply shedding its own skin, crumbling under the relentless, invisible grip of the red planet it circles. The grooves of Phobos are therefore more than just surface features. They are the visible expression of a deep and ongoing struggle between a moon and its planet, a silent, slow-motion drama of gravitational domination playing out right before our eyes. While we have been scanning the surface and the atmosphere for clues, one of the most profound missions to Mars was listening not with microphones, but with one of the most sensitive seismometers ever sent to another world. For 4 years, NASA InSight lander sat quietly on the flat, dusty plains of Elysium Planitia, its instrument deployed to the ground like a stethoscope pressed against the planet's chest, listening for its heartbeat. What it heard was a symphony of rumbles and cracks, a revelation that Mars is far from a dead world. It recorded over 1,300 seismic events, a steady drumbeat of Marsquarks that confirmed the red planet is still geologically active. This was a monumental discovery in itself, but the nature of these quakes held even bigger surprises, forcing us to rewrite our understanding of what drives a planet's internal engine. The first major puzzle was the source of the shaking. On Earth, the vast majority of earthquakes are caused by the slow, grinding movement of tectonic plates. For decades, we assumed Mars, being a smaller planet, had cooled off long ago and its tectonic activity had ceased. The Marsquarks detected by InSight largely confirmed this lack of plate tectonics, but they presented a new and compelling origin story. The majority of the larger quakes were traced back not to the boundaries of shifting plates, but to a single, massive region, Medusa Fossae. This is a vast, geologically young network of parallel fissures, trenches that slice through the landscape like scars from a giant's claws. It appears that this area is the most seismically active spot on the planet, a place where the Martian crust is still stretching and cracking. But what force is powerful enough to rip open the ground on a planet without plate tectonics? The leading theory points to the deep, slow, and inexorable process of planetary cooling. Mars is still shrinking. As its molten core continues to cool down over billions of years, it is slowly solidifying and contracting. This global contraction puts the entire crust under immense strain, like the skin of a grape wrinkling as it dries into a raisin. The crust, unable to compress evenly, eventually fractures at its weakest points. Medusa Fossae is one of those colossal weak points, a place where the planet is literally cracking open due to the stress of its own cooling. This makes Marsquarks fundamentally different from most earthquakes. They are not the result of sideways plate motion, but the sound of a whole planet tightening its belt, a testament to the slow, billion-year-long process of heat lost from its interior. The seismic waves themselves acted like a form of planetary sonar, allowing scientists to peer deep into Mars for the very first time. By analyzing how these waves traveled through the planet, how they were reflected, refracted, and slowed down, the InSight team could paint a rough picture of the Martian interior. The data revealed a planet with a structure both familiar and bizarrely alien. The crust of Mars turned out to be surprisingly thin and fragmented, more like a cracked eggshell than a single thick layer. It's estimated to be anywhere from 24 to 72 kilometers thick, which is considerably thinner than Earth's continental crust and suggests Mars may have lost more of its internal heat than we previously thought. Beneath this, the mantle is largely dormant, a thick, stagnant lid that doesn't churn with the vigorous convection currents that drive Earth's geology. This lack of active mantle convection is the key reason Mars has no plate tectonics and a much weaker magnetic field. But the biggest revelation was saved for the very center, the core. The seismic waves that passed through it indicated a core that is surprisingly large, liquid, and less dense than predicted. With a radius of about 1,830 kilometers, it is significantly larger relative to the planet than Earth's core. More startlingly, it appears to be composed of a liquid iron-nickel alloy that is heavily diluted with lighter elements like sulfur, oxygen, and carbon. This core is not the dense, solid inner sphere we might have expected, but a molten, relatively light ball that sloshes slowly within the planet. This composition explains why Mars's global magnetic field died billions of years ago. A liquid core needs to be churning vigorously to generate a strong magnetic dynamo, and the presence of so many light elements may have altered the convection processes, leading to a quieter, more sluggish interior. The Mars quarks, therefore, gave us the first direct measurement of another planet's core, a finding that will shape our models of planetary formation for decades to come. The different types of quakes also told their own distinct stories, painting a picture of a world with a complex geological personality. InSight detected two primary categories of Mars quarks, low frequency and high frequency. The low frequency quakes were the deep, powerful events, the ones that traveled through the planet's mantle and gave us our clearest glimpse of the core. These are thought to be the true tectonic quakes, originating from the deep-seated stresses of global cooling and crustal stretching. The high-frequency quakes, on the other hand, were shallower, more numerous, and their signals were much more scattered and crinkled. For a long time, their origin was a mystery. Why did these quakes have such a peculiar, high-pitched character? The answer, it turns out, was not coming from the deep interior, but from right near the surface. Scientists realized that the seismic waves from these shallow quakes were being scattered and distorted by a thick, fragmented layer in the upper few kilometers of the crust. This layer is a chaotic jumble of fractured rock, likely shattered by billions of years of meteorite impacts. It acts as a seismic diffuser, taking a clean signal and turning it into a messy crackle. This discovery was more than just a solution to a seismic puzzle. It revealed that the very top of Mars is a geologically complex zone, a rubble pile created by eons of bombardment, a layer that preserves the violent history of the early solar system. Listening to the persistent, faint rumbles of Mars has fundamentally changed our perspective. It showed us that a planet doesn't need to be tectonically vibrant like Earth to have a voice. Even a world quietly cooling in the cold of space has its own language of creaks and groans, a subtle soundtrack that tells the story of its deep, hidden structure and its long, slow journey toward geologic silence. Amidst the vast, rust-colored canvas of Mars, certain features leap out with such stark contrast that they demand an immediate and thorough investigation. One of the most visually arresting of these is a feature known informally as white rock, a bright, almost luminous patch sitting inside Pollack crater near the equator. From orbit, it looks like a splash of white paint in the middle of a sea of dark red, an island of brilliant material completely isolated from any other similar geology for hundreds of miles in every direction. Its official name is a mundane catalog number, but its appearance is anything but ordinary. The initial mystery was straightforward. in a landscape universally defined by iron oxides that paint everything in shades of ochre and brick. What could possibly be so brilliantly white, and why is it sitting alone in this one specific crater? The leading theories point to a story of erosion and exposure, but the details of that story are where the true scientific puzzle begins. The most widely accepted idea is that white rock is not a rock formation in the traditional sense, but what geologists call an erosional remnant. Imagine a situation where the entire floor of Pollack crater was once filled with a thick layer of soft, colored material, perhaps a deep deposit of volcanic ash that settled here after a colossal eruption, or a massive playa of sulfate and chloride salts that precipitated from an ancient evaporating lake. Over millions of years, the relentless Martian wind, acting like a planetary sandblaster, scoured away this entire layer from the vast majority of the crater floor. But in one central area, the material was either slightly harder, more thickly deposited, or protected by some long-vanished feature, allowing it to resist the erosion. The result is what we see today, a solitary mesa, a towering butt of white material that stands as the last witness to a deposit that once filled the entire basin. It is the geologic equivalent of a lone pillar left standing after the rest of the cathedral has crumbled to dust. This theory is compelling, but it immediately raises a more complex question. What precisely is this bright substance made of? The leading candidates are volcanic ash and sulfate salts, and each possibility tells a dramatically different story about the history of this region. If white rock is a compressed and cemented layer of volcanic ash, its story is one of fire and air. It would mean that a giant volcanic plume from a nearby vent, like one of the volcanoes in the Tharsis region, once carried an immense load of fine, glassy ash high into the atmosphere. Prevailing winds then transported this ash cloud, and it settled like snow, blanketing Pollack crater in a deep, pristine layer that could have been dozens or even hundreds of meters thick. Over time, this loose ash could have been cemented into a soft, white rock called a tuff by minerals carried in groundwater. The alternative, and perhaps more intriguing, possibility is that it is a massive deposit of sulfate salts. On Earth, when large bodies of water evaporate, they leave behind dazzling white crusts of minerals like gypsum, epsomite, or other sulfates. If white rock is composed of these materials, its story is one of water and its disappearance. It would suggest that Pollack crater was once home to a substantial, long-lived lake. As the Martian climate dried out and this lake evaporated, it became an increasingly salty brine, eventually precipitating a thick layer of crystalline salts across its floor, a fossilized bathtub ring on a colossal scale. The subsequent wind erosion then carved this salty deposit into the magnificent, isolated mesa we observe. Data from orbiting spectrometers has added clues but has not yet provided a definitive verdict. The mineralogy does seem to point towards sulfates, but the specific type and purity remain ambiguous. The debate is crucial because the two origins have vastly different implications. A volcanic ash origin tells us about atmospheric circulation and explosive volcanism in Mars's past. A sulfate salt origin, however, is a direct proxy for past water and a lot of it. It would mark Pollack crater as a site of a former habitable environment, a place where the chemistry could have been right for life to emerge. The very whiteness of the feature is itself a clue. It hasn't been stained red by the iron oxides that coat the rest of the planet. This suggests it is either composed of a material that doesn't readily react with iron, or it is a very young feature that hasn't had time to be covered by dust. Given the slow rate of dust accumulation on Mars, most scientists lean towards the former explanation. The material itself is inherently non-reactive and resistant to acquiring the classic rusty hue. The isolated nature of white rock adds a final layer of mystery. Why is there only one? If this was a regional process of ash fall or lake formation, we would expect to find similar white deposits in other craters across a wide area. Yet white rock stands alone. This uniqueness suggests that the conditions that created it were themselves a rare and special occurrence. Perhaps Pollack Crater had a unique groundwater source that welled up to form its lake long after the surrounding region had dried out. Maybe its specific depth and orientation made it a perfect trap for wind-blown volcanic ash, accumulating a deposit far thicker than anywhere else. The answer likely lies in a combination of global processes and very local, specific geology, a reminder that while we often study Mars as a whole planet, its history is written in a patchwork of unique local environments, each with its own story to tell. White rock, therefore, is more than just a beautiful anomaly. It is a monument to a specific and dramatic chapter in the life of Pollack Crater, a chapter that we are still learning how to read. We now turn from the mysteries of listening to the planet's heartbeat to a colossal feature you can actually see from orbit with a good telescope: Olympus Mons, the tallest volcano in the entire solar system. It's a monument of such staggering scale that it defies easy comprehension. This is not a steep, conical peak. It's a shield volcano, a gently sloping mountain built from countless layers of runny basaltic lava, much like the volcanoes that formed the Hawaiian Islands. But Olympus Mons is in a class of its own. It stands 21 kilometers high, nearly 2.5 times the height of Mount Everest. Its base would engulf the entire state of Arizona. The sheer volume of lava that must have poured out over millions of years to construct this leviathan is almost beyond calculation. And that very scale is what creates one of the most persistent and counterintuitive geological puzzles on the planet. When you have a volcano this enormous, you would naturally expect to find an equally enormous amount of debris surrounding it, a sprawling apron of volcanic ash, jagged blocks of hardened lava, and fields of coarse rubble blasted from its vents during its long, violent history. Yet, when we survey the vast plains that stretch away from the base of Olympus Mons, we find something startlingly different. The landscape is surprisingly clean. There are no vast, chaotic fields of volcanic ejecta. Instead, the transition from the mountain's base to the surrounding flatlands is often abrupt and remarkably smooth. It's as if the solar system's most prolific artist spent eons painting a masterpiece, but someone meticulously cleaned up all the paint splatters and discarded brushes, leaving only the pristine final canvas. So, where did all the mess go? The leading theory to solve this puzzle points directly to the unique properties of the lava itself. Olympus Mons is a shield volcano, and its eruptions were likely dominated by what geologists call effusive activity. This means the lava that built the mountain was extremely fluid and low in viscosity, much like the basalt that flows from Hawaiian volcanoes. This runny lava doesn't explode violently, it oozes and spreads. Instead of trapping gases and building up pressure that leads to catastrophic blasts, the gases in this thin lava can escape relatively easily. The result is not a sky-darkening plume of ash and rock, but a relentless flowing river of liquid fire. Think of the difference between opening a shaken can of soda, which erupts violently, and simply pouring soda from a bottle which flows smoothly. Olympus Mons, for the most part, was a pourer, not an exploder. This style of eruption would produce immense sheet-like lava flows that stack up layer upon layer, building the mountain's characteristic broad profile, but it would generate very little of the coarse, chunky debris known as pyroclastic material. The primary debris from such an eruption is the lava flow itself, which hardens into a solid, relatively smooth layer of rock. Over millions of years, these countless flows have created the vast, gentle slopes we see, effectively burying their own rubble under newer and newer layers of basalt. The mountain, in a sense, is its own debris field, but it's been neatly paved over by its own subsequent activity. However, this cannot be the entire story. Even the calmest shield volcanoes on Earth have sporadic explosive phases, especially if groundwater seeps into the volcanic plumbing system, flashing instantly to steam and causing a violent steam blast. A volcano the size of Olympus Mons, active for hundreds of millions of years, would have almost certainly experienced such explosive episodes, so where is that evidence? This is where the otherworldly environment of Mars comes into play. The planet's low gravity and thin atmosphere would have profoundly altered the distribution of any explosive debris that was produced. On Earth, ash and rock fragments ejected from a volcano fall back to the ground relatively close to the vent, piling up into recognizable ash layers and aprons. But on Mars, with only 38% of Earth's gravity, the same explosive force would launch material much farther and higher. And with a thin atmosphere offering little resistance, the finest ash particles could potentially be dispersed across global, even planetary, distances. A significant explosive eruption at Olympus Mons might not have deposited its ash neatly around its base. It could have sent a fine, dusty haze around the entire planet, settling as a thin, uniform layer that would be incredibly difficult to distinguish from the omnipresent wind-blown dust that coats Mars today. What looks like a missing debris field might, in reality, be a debris field that was pulverized and spread so thin and so wide that it simply blended into the background. You wouldn't see a pile of sand next to the mountain. You'd see a single grain of sand on every beach on the planet. Another compelling piece of this puzzle involves the relentless forces of erosion that have been at work for billions of years. While Mars lacks the liquid water erosion that dominates Earth, it is a world sculpted by wind. The same sand-blasting winds that carve the intricate patterns of the Medusa Fossae formation have been scouring the flanks of Olympus Mons for eons. Any loose, fine-grained volcanic ash that did settle around the base would have been the first material to be picked up and carried away by these persistent winds. This material wouldn't vanish. It would simply become part of the global dust cycle, eventually settling in other regions of the planet, perhaps even contributing to the immense dust deposits found elsewhere. Furthermore, there's a fascinating possibility that some of the missing debris is actually hidden in plain sight. The vast, smooth plains that surround the giant volcanoes of the Tharsis region, where Olympus Mons resides, are themselves made of ancient lava flows. It's possible that later, massive floods of extremely fluid lava, erupting from fissures on the flanks of the volcano or from nearby sources, simply inundated the older, rougher debris fields, burying them under a smooth, young blanket of basalt that we see today. The evidence of the volcano's violent youth could be entombed beneath these placid plains, waiting for a future mission with ground-penetrating radar to discover it. The mystery of the missing debris, therefore, isn't a single missing piece, but a complex interplay of volcanic personality, planetary physics, and eons of environmental polishing. It forces us to see Olympus Mons not just as a static mountain, but as a dynamic system that both created and then systematically erased its own construction site, leaving behind only the magnificent and deceptively clean final product. Even as we contemplate ancient volcanoes and deep planetary groans, there is a clear and present reminder that the surface of Mars is a place of constant, if subtle, change. For decades, we imagined the Martian landscape as a frozen snapshot, a still life painted in dust and rock. But high-resolution cameras in orbit have shattered that illusion, revealing a world that is still actively being reshaped. Among the most compelling evidence for this modern dynamism are the shifting sand dunes. Here on Earth, we think of sand dunes as slow-motion travelers, creeping across deserts over the course of years or decades under the force of robust winds and a thick atmosphere. On Mars, with an atmosphere only 1% as dense as Earth's, you would expect any dune movement to be glacial if it happened at all. Yet, time-lapse images taken by orbiters like the Mars Reconnaissance Orbiter over the span of several Martian years have captured something astonishing. Dunes are on the move. They are crawling across crater floors, marching down valleys, and reshaping their crests at rates that, while slow by terrestrial standards, are far faster than anyone predicted. Some Martian dunes, those classic crescent-shaped formations, have been clocked migrating several meters in a single Earth year. This is not a hypothetical process. It is a measurable, ongoing activity, and it presents a fascinating puzzle in physics. How can a whisper-thin atmosphere, barely capable of feeling like a breeze, push around vast mounds of sand? The answer lies in a unique combination of environmental factors that make Martian aeolian processes a world apart from our own. The first key is the nature of the sand itself. Martian sand grains are not like the smooth, rounded quartz grains found on a terrestrial beach. They are often smaller, finer, and more sharply angular, a product of billions of years of bedrock being shattered by impacts and weathered by the harsh, dry environment. This smaller size and irregular shape makes them easier for the wind to lift. More importantly, the low air pressure of Mars changes the fundamental physics of sand movement. On Earth, a grain of sand has to fight its way through a thick soup of air molecules, requiring a substantial gust to become airborne. On Mars, with far fewer air molecules in the way, the threshold for movement is dramatically lower. A wind speed that on Earth would be barely perceptible can, in the thin Martian air, be enough to initiate saltation, the process where sand grains make short, hopping jumps along the ground. Once a grain is lifted, it can travel farther on each hop because of the reduced drag, and when it smacks back into the dune, it can dislodge several other grains, creating a cascading effect. It's a classic case of a little effort going a long way. The low-gravity environment also means each grain weighs less, making it that much easier to displace. This efficient, low-energy sand transport means that even the modest prevailing winds of Mars, which are constantly blowing, can achieve what on Earth would require a storm. But this discovery does more than just solve a physics riddle. It turns the dunes into a powerful scientific instrument. These migrating sand mountains are giant natural wind vanes. By meticulously measuring the direction and speed of their movement from orbit, scientists can create detailed maps of current surface wind patterns across the entire planet. The dunes tell us which directions the winds blow most frequently and with the most force in a given region. This data is invaluable for testing and refining our global climate models of Mars. It helps us understand how the atmosphere circulates heat and dust on a seasonal basis, and it reveals local wind systems that are generated by the interaction between the atmosphere and specific topographic features, like the slopes of a crater wall or the flank of a massive volcano. Furthermore, the movement itself is a form of active geology. As dunes migrate, they can bury small-scale surface features like ripples or even small rocks, effectively resetting the clock on that patch of ground. This has direct implications for missions like the InSight lander, whose solar panels were gradually covered by dust, and for planning future human settlements, where understanding sand drift is crucial for preventing the entombment of infrastructure. The observation of moving dunes conclusively shatters the old idea of a geologically dead Mars. It proves that the planet is not merely preserving a history written billions of years ago. It is writing a new chapter today in sand, one grain at a time. But perhaps the most ethereal of all Martian phenomena are the ones that appear only in the deepest darkness, high above the surface where the thin air meets the void. Orbiting spacecraft have documented the existence of rare, high-altitude night clouds, delicate veils of ice that form dozens of kilometers above the ground. These are not the dust-laden clouds of the daytime. They are composed of tiny crystals of carbon dioxide ice or water ice, so fine they are often invisible until the sun dips below the horizon. Then, in the twilight or the deep night, they catch the last rays of the sun, glowing with a faint, ghostly luminescence against the blackness of space. It's a beautiful and purely physical phenomenon, a dance of light and ice in the upper atmosphere. Yet, the sheer otherworldliness of this sight has sparked one of the most captivatingly speculative ideas in all of Martian science: a hypothesis that resides squarely on the fascinating boundary between established fact and thrilling fringe possibility. What if that gentle glow wasn't just reflected sunlight? What if somehow it was light being generated from within? This line of thinking leads to a concept that sounds like it's straight from a novel, the idea of bioluminescent Martian clouds. The theory is this: if microbial life exists on Mars, its last, most tenuous refuge might not be in the deep subsurface, but high in the atmosphere. On Earth, we find extremophile bacteria thriving in the upper reaches of our own skies, carried aloft by winds and existing in a suspended state. Could a similar, hardy form of Martian microbe have adapted to survive in the cold, thin, but UV-rich environment of the upper atmosphere? And if so, could those microbes, through their metabolic processes, produce a faint collective glow, a bioluminescent signature visible from space? It's a breathtaking thought, the image of the entire red planet adorned with a living, shimmering crown in its night sky. Now, it is absolutely crucial to state that this is firmly in the realm of highly speculative fringe science. There is not a shred of direct evidence to support it, and the vast majority of planetary scientists regard it as an intriguing thought experiment rather than a serious research proposal. The observed luminescence is perfectly and completely explained by the well-understood physics of scattered sunlight from ice crystals. To invoke biology is, from a strict scientific standpoint, entirely unnecessary. These clouds are almost certainly a beautiful but sterile meteorological event. However, the reason this idea persists in the imaginations of some researchers and science enthusiasts isn't because it's likely, but because it forces us to confront the very limits of our scientific paradigms. It challenges us to ask, how would we even know? If we one day saw an unexplained, faint glow in the Martian night that didn't match any known cloud model, would our instruments be sensitive enough to distinguish its spectral signature from a known chemical process? This speculation serves as a powerful reminder that our search for life is often constrained by what we expect to find based on our Earth-centric experience. We look for fossils in rocks, for organic molecules in drilled samples, for methane seeping from the ground. We are, in essence, looking for life that acts like life on Earth. The concept of atmospheric bioluminescence pushes us to consider a form of life that is not just surviving, but actively signaling its presence in a way we hadn't anticipated, a form that has found a niche in one of the most unexpected environments imaginable. This dance between the solid ground of established science and the alluring horizon of the unknown is the very engine of exploration. For every one of the 30 phenomena we've explored, from the confirmed reactivity of the soil to the potential for subglacial lakes, there exists a spectrum of interpretation. On one end lies the conservative, most probable explanation, the one that fits neatly into our current models without requiring any dramatic new physics or biology. On the other end lies the radical, the extraordinary, the idea that would force us to rewrite the textbooks. The true work of science is to navigate this spectrum carefully, to test the fringe ideas with rigorous data until they are either elevated to the status of fact or gently retired. The speculation about glowing clouds is a perfect example of this process. It is not a claim but a question. It is a tool for stretching our imagination, for probing the boundaries of the possible. It ensures that as we continue to map the canyons and analyze the rocks of Mars, we also remember to look up into the twilight sky and wonder if the greatest secret of the red planet might not be buried in its past, but floating silently and perhaps even shining in its present. And with that, we have journeyed through 30 of the most compelling, bizarre, and thought-provoking mysteries that Mars has to offer. From the chemical whispers in its soil to the groans of its deep interior, from the ghosts of ancient dunes to the dynamic ice of its poles, this world has proven to be a master of disguise and a perpetual source of wonder. Each mystery solved seems to unlock two more, ensuring that our celestial neighbor will continue to captivate, challenge, and inspire us for generations to come. The conversation is far from over. In many ways, it has only just begun. And so our journey across the rust-colored plains and through the whispering atmosphere of Mars comes to a close for now. We have wandered from the tantalizing, debated plumes of methane to the dark, creeping fingers of the recurring slope lineae, from the psychological phantom of the face to the ironclad time capsules of the blueberries. We have scaled the solar system's greatest volcano, Olympus Mons, and puzzled over its missing debris, then plunged into the fractured anarchy of the chaotic terrain, evidence of planetary-scale floods. We have listened to the groans of Marsquarks, revealing a liquid core, and gazed upon the reptilian skin of the dragon scales, a billion-year-old climate record. We have seen the polar spiders spawn in explosive jets of gas and watched the sand dunes themselves slowly march across craters, from the hidden, potential lakes deep under the ice to the bizarre seasonal breath of oxygen that defies explanation. One thing has become undeniably clear: Mars is not a dead world. It is a world of profound and active processes, a complex system of geology, chemistry, and climate that continues to operate in ways that constantly challenge our Earth-centric expectations. Each of these 30 phenomena is more than just a curiosity. It is a pointed question, a direct challenge to our models and our imagination. They are the unfinished sentences in the story of a neighboring world, and it is in the gaps of our understanding that the most exciting science happens. These mysteries are the fuel for the next generation of rovers, the orbiters with ever sharper eyes, and the daring sample return missions that will one day bring a piece of the red planet back to our labs. They are the reason we keep looking, keep questioning, and keep designing new ways to listen to the subtle heartbeat of another world. The collective force of these enigmas ensures that Mars will remain a central character in humanity's greatest story, the search for our place in the cosmos. It pushes us to refine our technology, to collaborate across nations, and to train the scientists and engineers of tomorrow. Now we turn the question over to you. After this tour of Martian puzzles, which one captures your imagination the most? Is it the haunting possibility of a subglacial lake, a hidden sanctuary for life? Or the sheer, violent drama of the chaotic terrain, a landscape torn apart by escaping oceans? Perhaps it's the simple, perfect sphericity of the blueberries, or the seasonal magic of the dark dune spots. Let us know in the comments below which mystery you would most want to see solved. Your curiosity is part of this grand exploration. If you enjoyed this deep dive into the cosmos's greatest puzzles, make sure to subscribe and hit the notification bell. Our journey through the universe is just beginning, and there are countless more wonders waiting to be uncovered.